And so Kaito is built using the classic Kubernetes operator design pattern. And what that means is you're basically going to interface, or your user experience with this Kaito thing is YAML. What does that mean if you have YAML? Well, that means it's just a code file. If it's a code file, that means I could check into my repository, and it becomes really GitOps friendly to kind of like bootstrap the infrastructure into your environment, right? And so just to give you a quick high-level overview of what this is, the operator allows you to declaratively express your intent in how you want to run an open source model, right? And so when you install Kaito, what you're going to eventually install is the workspace controller and a node provisioner, right? And the user doesn't have to worry about all this other stuff going on in the background. The user only has to worry about one custom resource, which is the workspace. I'll show you a workspace in a little bit, but the workspace basically allows the user to say, hey, I want to run a Mistral 3 or a Gemma 3 model, open source models, and run that all locally within my cluster. Now, some folks can just take advantage of the model as a service, like OpenAI endpoint and all that stuff. There are other organizations that is a little more sensitive to data leaving the cluster, so they want to keep everything in cluster. So this is going to be a great way to achieve that, okay? And so Kaito allows you to basically write a workspace manifest, submit it into the Kubernetes API server, and then as soon as that happens, the workspace says, yes, I see you want a, I don't know, 5.4 mini model. Let me go put out a node claim, right? A node claim is basically a resource within the whole Carpenter project. So it does leverage Carpenter. And so the node provision will say, okay, I need to go get a SKU, a GPU node, which could be a SKU in the cloud. And it'll actually go pull that, provision a virtual machine, do all the necessary infrastructure work like installing the NVIDIA device plugin and all that other stuff, and then attach it to your Kubernetes cluster. And then once that is there, it'll actually schedule the workload, which is going to be the inference service. That inference service is actually in a container, and it gets deployed and scheduled just like any other Kubernetes resource. And so at the end of it all, you get an OpenAI compatible endpoint serving your model. And the inference runtime that it uses by default is using the VLLM runtime. VLLM is a very popular open source inferencing engine, but it also supports Hugging Face transformers as well, so you do have an option there. But the default is VLLM, and I suggest that you just stay there, okay? And so what this allows you to do is, it really allows you to go from 0 to inference in just a few minutes with literally just like a few lines of YAML, right? So as a user, you could even pick one from one of the presets. Presets are like YAML manifests that have already been written for you. All you do is say, yep, click and deploy, right? And so a lot of the popular open source models are there. And so you just do kubectl apply, and boom, off it goes. It's there in a few minutes. What I want to do next is just show you how to just see it in action and how to get rolling with this. So let me just break out of this slide real quick and then flip over here. Let me open this up. Probably the easiest way to get going as soon as you have Kaito installed. Okay. As soon as you have Kaito installed in your cluster, probably the easiest way to get started with working with the workspace is probably from the Headlamp project. Has anybody here heard of Headlamp? Okay, a few people. If you're just getting started with Kubernetes and you're more of like, I need to see this from a GUI perspective, Headlamp is an open source project. It was actually donated to the CNCF, so it's a CNCF project now, and it's like the de facto Kubernetes dashboard at this point, right? And so Headlamp is really awesome because it has a very strong plugin architecture, and so you can literally install whatever plugin you need. And so Kaito actually has a plugin for Headlamp. And so if you just search for the plugin Kaito, you just install that into your cluster, and you can pretty much work with your Kaito resources. And so if I connect to this cluster over here, which is running in Azure and it has Kaito installed, I can scroll down and I can immediately see my Kaito workspaces. You can see I deployed 2. And I can start to browse through the model catalog. So these are all the presets that I mentioned. So these are all the pre-configured model deployments that you can choose to basically deploy. And the YAML here is already written for you, and it's only a few lines of YAML. So you can review and deploy that, but I already have that, so I can just start chatting with my model right away. So if I just pick one of my models here, 5.4 mini instruct, and I say hi, because we need to be nice to the AIs, I can say something like, can you tell me about the SCaLE conference? And then it'll come with some gibberish answer, because it doesn't really know what I'm talking about. And yeah, it looks like it really doesn't know, because it's trained on data from 2023 or so, right? So quick and easy way to get started with models running inside your cluster, but we need to do more than that, okay? So if I move on here, back to the slides, and we move on, the other thing that Kaito also offers is it offers this RAG engine controller that you can install. And it's completely separate from the workspace, but you can use those two together, okay? The RAG engine is basically just another custom resource that you deploy into your cluster, and it's just as short, like YAML-wise. It's only like 16 lines long. And the way it works is like this. RAG engine controller listens for custom resources that you deploy in the cluster, and you say, hey, I want a RAG engine that's gonna basically spin up my entire RAG service, so everything that you see on the right there, all that gets spun up with your one single manifest, right? So you're getting the vector database, the local embedding service, and the open AI compatible inference service, right? And so what does that give me? Well, that gives me the opportunity to basically, oops, if I go back, to basically use the OpenAI compatible inference, because remember we said that we want to query the RAG service, have it retrieve documents, and then send it over to the LLM, like notes, open notes for the test. And so that's what we want to do. And so that's what I'm going to demonstrate in this sample application for you, okay? So what is this sample application? It's just a chatbot. I know we're probably all tired of seeing chatbots at this point, but here we are. We are looking at a chatbot architecture. And the way it works is, it has a front-end web UI and a back-end service, all hosted on a Kubernetes cluster, naturally. When a user wants to interact with the chatbot, they're actually going to come through the Istio ingress gateway, and that's going to send the request down to the web UI. The web UI is where all the I guess AI requests will go, and that's actually going to flow through my agent service. The web UI is built using Next.js. Agent service is written in Python using the Microsoft Agent Framework. And because I'm using the Microsoft Agent Framework, I get a lot of the observability tooling out of the box. And so I have an OTel collector in my cluster that's going to send all of my observability metrics down to a Grafana looks good to me stack, right? And then I can have chat history and all that good stuff stored into my Redis session. But that's, aside from everything else, the thing that we want to focus in on is this Kaito gateway that I have installed. Because we have Istio installed here, I'm running a gateway API in there, and that's going to allow me to route between the two different services, right? RAG engine and workspace. So that's the high-level architecture of this. And look, we're going to take a look at the app, right? So we're going to see how we can take this app and see it progress from it not having context of the SCaLE conference to grounding it with real data, and then having it give us real answers that's actually actionable for us. And we're going to do it live. So I have I have a lot of the infrastructure kind of like half-baked, but the application is not there. And I thought this was funny because last year I was doing a talk and I had a lot of problems with the internet. And I had to fall back to recording. But we're going to try this, and we're going to see how it goes. So just to reset one more time, because I'm going to progress through, and I'm going to show you a lot of different things along the way. So again, the workspace. The workspace is the smallest unit of inference within the whole Kaito project. You get a node, you get a deployment, you get a pod, you get a service, you get an open AI compatible endpoint, right? It's all pretty simple Kubernetes stuff at that point, right? What's new is this whole concept of an inference set. It's more of a higher level abstraction for workspace. And you would actually want to use the inference set for dynamic model routing, which we're using, and for inference scaling with Kata if you need to, right? If you need to scale out your model. But the workspace, again, is fundamental and foundational for this whole thing, right? Because, like I said, you're going to get a node, you're going to get a deployment and service. So it's all very simple Kubernetes at that point, okay? Next, let's talk about routing. So for routing, I'm actually using the Gateway API inference extension. This is actually an extension built on top of the whole Gateway API project. And it basically enables you to do dynamic routing for models because, you know, there's no one model fits all type scenario. You want to use different models for different jobs. But what you don't want to do is you don't want to set up multiple gateways for each model. And so with the GIE or the Gateway API inference extension is you can now do body-based routing, right? And so you can, in the request body, you send what model name you want, and it'll know how to do the routing to the appropriate model. And so what we get is something like this. The user says, hey, I want to make an inference request. The user doesn't really have to tell what model it wants. The application will know that. And so it goes to the Gateway API inference extension, and it says, oh, you want the Gemma 3 model? OK, you go over there. That's where the model is, and that's the way it's going to work. Okay? And so let me show you, jump into another demo, and show you how this Gateway API inference extension actually works. So what I will do is I will port forward. Actually, I'm going to port forward that. And clear. Oops. Clear. I will port forward to my Kaito Gateway inference extension, and it is up and running. And so what I can do essentially is this V1 chat completion, this is basically an OpenAI compatible endpoint. I'm pointing to my localhost on 4000 because I port forwarded that. And then I am basically saying, hey, I want to make a request to the 5.4 mini model, right? And so if I go ahead and send that request over, it's going to come back. And I always chuckle to see what it gives me. So SCaLE is a prestigious high school level academic competition. OK, yeah, that's completely wrong, right? So that's not the model that I want for the job. The model that I want, let's try the Gemma 3 model, right? So same exact endpoint, same exact host. All that's different is the model that I'm calling into, right? And so the routing is happening appropriately, and then I get a response back. Let's see. OK, here's a comprehensive overview of the SCaLE conference, the Southern California Linux Expo. Hey, that's better. So models do matter, right? So that is great. Now, can I ask it a follow-up question? So can I ask it a question like, hey, will there be any sessions on Kaito at the conference? So same exact endpoint, going back over to the Gemma 3 model. Let's see. It's going to come back, and it says, yeah, sure. The SCaLE 2024 conference schedule has Kaito. So here we go. Now it's not telling the truth again. We need to actually fix this, right? So how do we fix that? Go back over to the slides here. We do this by basically adding the RAG component and then routing the entire application through the gateway, right? And so I'm going to take my application, I'm going to hook it up to the Gateway API, and the Gateway API will basically know where to send the traffic to. And so if I jump over to my, oops, oh, no, I didn't want to do that. I want to bail out of here. Let's jump over here, and my application is out of sync. So let's just go ahead and sync it real quick. And we'll wait for that. So while that is waiting and deploying, I'm going to show you just a little bit of source code for the application. So the web app isn't really anything special. All it does is basically route all AI requests over to the agent service that's running in my cluster. The actual agent itself is written in Python. And so if I just scroll down here, I have instructions. Where'd the instructions go? So here's my observability bits there, and there we go. So how do I word wrap this? Boom, word wrap. Okay, there we go. So I have instructions for my model, and I'm saying, hey, you're an expert at Linux and free and open source software. You know everything about the SCaLE conference and the scheduling and all that good stuff. So, and it's also saying, you know, hey, always cite relevant sessions by providing their titles, locations, right? But our application can't really do that yet. And let me show you. So if I head over to this website, chat.aksrocks, I can say hi, because we want to be nice to the AI. And this is the awkward part where we wait for the AI. Okay, so it says, okay, yay, I can help you with anything related to free and open source software at SCaLE 23x. So I say, will there be any sessions on Kaito? Will there be any sessions on Kaito? Let's see. We know the answer. It's going to be no. But let's just see this through. Okay, it's thinking. Thinking. There we go. All right. So it's saying, yeah, there is a session. There's actually two. Wow, there's two, huh? But these are from like 2 years ago, 2024. And was Kaito even out then? I don't even know. And they have links, and these links probably go nowhere because they don't look familiar to me. So we are definitely going to go fix this, okay? And so the way the RAG engine is going to work is it's just another custom resource. And it functions almost exactly like a workspace, but with a little bit of a difference in that it can pass through to the actual LLM endpoint, right? And so the thing that you see on the right here, that was the workspace. That's what we kind of like talked through and worked through. So you get a node deployment service, right? When you deploy a RAG engine, guess what? You're getting a node deployment and service, okay? And so the difference here is that the user is now interacting with the RAG engine service, right? Because everything is OpenAI compatible, I have very, very minimal changes I need to make in my application code. So now my app goes through the RAG engine service, it retrieves the relevant documents, and it sends those relevant documents over to my workspace. But guess what? It doesn't need to be a workspace. You don't need to use RAG engine and workspace together. If you have an OpenAI compatible inference service available somewhere else, you can definitely just forward that service to that somewhere else, and it'll work just fine. I'm just so happen to use both of these workspace and the RAG engine together, but just know that it's not a requirement there, okay? And so what I will do is, let's go show what the RAG engine looks like. So let me just bail out of here again, and let's close this, and let's stop port forwarding that. So what I will do is I will go ahead and, hold on, okay, port forward. There. So my RAG engine is named SCaLE 23x, and what I will do is I will open up my test file for RAG indexes, and basically I could just make a call on the /index endpoint just to see what I have in here. I have no data, right? And so what I'm going to do is this. I'm going to stop that. I'm going to do a Argo submit. So I have a workflow template. I'm just using Argo workflows for my indexing pipeline. And so I'll just go ahead and get that started. This is going to take a few minutes. Basically, it's going to download the entire SCaLE 23x schedule, and it's going to index that in my RAG index for me at real time. So while we're waiting on that, let's actually go look at what this is actually doing. So I do have a schedule project here, and I am parsing the schedule. And sorry, SCaLE folks, but I did go and scrape your website for all the presentations for this conference. And so this Python script just basically did that. It goes and builds out a JSON file, and then it formats the JSON file into a format that the RAG engine needs it to be in, right? And so if I just want to just show you example files of what that eventually looks like is when I go and pull down or scrape all the information, it looks like this pretty easy to read and follow JSON document. But when you want to index your JSON data into the RAG engine, it needs to be in a specific format. And all it needs really is the index name. Okay, and so here I'm just calling a schedule index. It could be whatever you want. And then an array of documents. And within that array of documents, I have the text. This actually becomes a document itself. And then I can plug in any metadata that I want, right? So here I'm just trying to shove as much information as I can into the index so I get a lot of relevant information coming back out, right? So things like the title, the description, the URL so that I can find more information about it, what room it's in, the time, all that other good stuff is everything that I really wanted to see here. So let's just check on the status of this. Okay, so it downloaded and is formatting now. So we'll let that continue. And let's go take a look at the actual RAG engine manifest. So you can see here, to deploy a RAG engine, that's it. It's just a handful of lines of code. And the important thing here is the instance type. So I'm running this in Azure, and so I wanted it on this specific GPU node. But here's a little tip. Like for RAG engines, you probably don't even need a GPU node. Embedding data doesn't require, it's not very compute intensive, so you can probably get away with it on a CPU-based node, but I'm just using this SKU here because I had access to it. The embedding model that I talked about, you can actually point it to a local, this would eventually be a local embedding model. It actually pulls it down from Hugging Face. But if you had like a remote embedding service available to you, you can actually point it to that. Probably the most important thing here is the inference service, right? So after the RAG engine retrieves all the documents, it needs to know where to send that request to. And so this is where I'm actually pointing it, and I'm saying, hey, you know what? Get those documents and send it right back out to my Kaito gateway, and my Kaito gateway will know what to do with it, okay? The other important thing here is context window size, okay? You do not want the RAG engines to send more context than the model can handle, and so this is where it gets a little dicey in that you need to know what the backend model context size could be. So think of a safe number there, okay? So now, let's see. Everything looks indexed. Everything is good. So if I do this, clear, and if I just port forward one more time to my 5002 SCaLE 23X service, and then let's go grab my test file one more time so I can send the request to the indexes. Boom, there we go. I have an index now. What can you also do with the RAG Engine API? Well, you can actually persist the indexes. The RAG engine can actually host multiple indexes, but it could only serve one at a time. So you can kind of like save this index and load them whenever you need to. So we can also do a get to retrieve all the documents. And so you can see here that a lot of this stuff was actually indexed, and you start to see all the session data. So that's great. Now, since we are port forwarding to the RAG engine, I can actually make a post call using the same OpenAI compatible endpoint, so V1 chat completions. And basically, I'm passing it the model name because we know the Gemma 3 works a little bit better. And then the index name, which is schedule index. And I'm asking it, will there be any sessions on Kaito, right? So I send that request, and let's see what it comes back with. So it's saying, yes, there will be a session on Kaito. The title is Rage Against the Machine. Yep, and there we are. That's me. We are in Ballroom A, so this is exactly what I want the LLM to do. Give me facts. Now, let's see. Let's push this a little further. Boom, 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 boom. And we can actually test it through the gateway now, okay? So if I jump back over to the RAG engine, you can see here, I want everything flowing through my gateway API, right? And so what I can do is, at this point, it's just normal gateway API routing. So I have an HTTP route, and I want it accessible at the /rag path. But I'm doing a little bit of, I wouldn't call it trickery, but I'm doing a little bit of URL rewriting. So anything that comes in on the /rag path, go ahead and do a URL rewrite, put the V1 back in, but this time send it to the SCaLE 23x service, which will basically funnel it back into my RAG engine service, okay? So if I do this, if I just do a port forward again, but I port forward back to my Kaito gateway, let's see, where did this test file go? And then if I scroll down here, so now you can see that the endpoint just changed just slightly. So instead of V1 chat completions, I'm doing RAG chat completions. Still going to the same index, same model, and I can actually test it behind the Istio gateway. And so if I submit that request, I'll get some answers back. And you can see here that, yeah, I'm getting the same correct answer back. This is the same session. That's great. And let's actually push our luck just a little bit and ask it a follow-up question. And just to test the metadata, and I'm asking it, hey, can you also provide me the URL for that session? And yeah, sure enough, the metadata is actually working, and it's saying, yeah, here's the URL. So if I click that, there we go. So that's the exact session that we are in, right? So where do we go from here? Well, oops, I need to go about it this way. There we go. So what do we do there? We basically index the documents, and when the user queries the RAG engine, we are embedding the original query, retrieving relevant documents, and sending that original query with the relevant docs to the LLM, right? And so this is kind of the flow path that I illustrated for you over here, is go to the RAG endpoint, goes to the RAG endpoint, retrieves the documents, sends it back to the gateway API, because the RAG engine didn't change. Everything goes to the gateway API, and the gateway API does the model-based, body-based routing to send it to the appropriate LLM. So now, let's do this. Oop, I went too far. Final test run, okay? So what we will do is, stop the port forwarding there, clear that out. Because I have my entire app is basically all GitOps based right now, all I have to do is basically just change the overlay that I'm deploying, right? So this is all being done in the ArgoCD environment. And so what I can do is git diff, okay? And so you can see I'm just changing it from my overlay was called direct, which is like just going to the direct gateway API. And so now I want it to route through the RAG. So that's basically all I'm doing. So if I do git add, git commit, and then a git push, it'll eventually go. And then I can do like ArgoCD app sync. We'll go ahead and sync that, because I don't want to wait for it. I just want it to just go. All right. Okay. That looks good. And I can do ArgoCD app sync chat, prune it too. And I don't know why I did this, but my app is actually using Argo rollouts, and I don't want to wait for that either, so I'm just going to force push Argo rollout. So I'm just going to force promote that. Okay, so while all that is actually being deployed out, let's just go take a look at the overlays just one time, just to kind of show you what the difference is. So in my actual app, this is why I had to sync two different things. I actually made the change over here, right? So I'm using the app of apps pattern for this. And so I'm saying, hey, deploy the chat app and use this specific overlay. It was direct, but I just changed it. I just flipped it over to RAG. And what that means is now that I'm going from the direct, which was pointing at the Kaito gateway slash V1 as my OpenAI endpoint, because I made this switch over to my RAG overlay, I'm now telling my agent framework application that the OpenAI API base is actually at /RAG, right? So this is kind of like the way I can implement RAG-based or grounded AI system into my application with very, very minimal application code changes, right? Because this is all OpenAI compatible endpoints at this point, okay? So let's just check on the status of where we are at. And if I do a get PO, okay, so I have my agent applications running. They're 100 seconds old. Okay, so this is good. This is good. So if I take that same question, paste it back in, and I ask it, will there be any sessions on Kaito, right? So now, just think about that diagram again. It's going through the RAG engine, getting the appropriate documents, coming back down through the Kaito gateway, and then sending that request off to the LLM. And here we go. I can already see that it's working. So it's like, yeah, you're right to ask again. My apologies. So the AI is nice to me. You be nice to the AI will be nice to you. That's the moral of the story, I guess. But that is the session that we're in. We are definitely in this room. It is this time. And the metadata is all working, right? And so just in a few minutes here, we got a glimpse of like how easy it can be to build AI systems and have it grounded on factual data, just all using Kubernetes resources. So would you consider that pretty easy? Hopefully. Okay. So key takeaways here is that context is everything, okay? RAG is a foundational tool to the entire AI stack, and it can be coupled with some of the other tooling and techniques that are available there, but RAG is definitely something that you should plumb in, right? But RAG pipelines can seem more like plumbing than the actual product, right? And so this is why you leverage a thing like Kaito and the RAG engine to help make the ease of adopting these technologies just a little bit simpler, giving you a nice shorter runway, if you will. And I would say leverage the gateway API extension within your AI systems because models matter, right? And you want to pick the right model for the right job, okay? The one thing that Kaito RAG engine will not give you is it won't give you a way for you to, I guess, extract and prepare your data for indexing, right? So that Argo workflow that I was running, that's just something that you're probably going to have to invent because each organization has data in different places and different processes. So that's not a concern that the Kaito team was looking to address there. So I would say, I mean, do something that, you know, kind of like what I did, start small, iterate, and yeah, go from there. So with that, I would say go ahead and try the demo out for yourself. If you scan that QR code, it'll take you straight over to my GitHub repo where I have this entire thing documented, and you know, you can actually read through it and go do the thing, right? Yeah, and I guess that is it. I don't know how much we are doing on time. I think we have 15 minutes for questions.
Did really well.
But yeah, these are some links that are available to you. They'll take you to all the Kaito docs around the things that we've described here. I would also call out that Kaito is a CNCF sandbox project, and so if you are on the CNCF Slack, there is a Kaito channel. They do run community calls every 2 to 3 weeks or so, and so go ahead and check that out. The chat application that I just demonstrated to you, it is actually live. If you want, you can play around with it over there, but just a little bit of fair warning, it's not meant to handle a lot of load. I think I'm only running like 2 replicas or whatever, so, but feel free, play with it, figure out what your next session would be. I'm probably gonna take down the application when I get home tonight, but other than that, yes, thank you for your time and attention.
Thank you, Paul. I guess I can ask the first question. How dense is the contributor and maintainers for Kaido today?
How do you?
How dense? How many folks are already involved in the
Oh.
maintainer and the contributor?
Yeah, primarily the contributors and maintainers are from Microsoft, and there's probably about, I don't know, like a handful of engineers, probably like maybe 6, maybe more. I mean, I'm just guessing. But yeah, but they're definitely putting in a lot of work and cutting releases. They just cut the 0.9 release, I believe, like a week ago, and it's moving pretty fast. So yeah.
All right. Open for questions.
Hi. Yeah. So is this like a sandbox for learning, or is this something that you can take as a template for a production rollout?
This is definitely a production-ready system. It's meant for you to run pretty large-scale open source models within your cluster. I just so happened to build a chatbot on top of it, using some of the techniques that is available through Kaito, but it's definitely production-ready. And as I just briefly mentioned, with the whole inference set concept, you can have like distributed models. You can also scale based on Kata metrics. So yes, it is definitely meant for production.
Follow up also on when you pull the code down, can you run it on a laptop with Kind, or because I saw that there are hooks for GPU.
Yeah.
Is that necessary that you have something outside that's a GPU server?
Not necessary. The original implementation was to kind of like leverage the GPU provisioner and have it go pull or provision an Azure GPU. You don't need to do that. If you want to basically implement your own workspace template, you can point it to an existing node. So there's a node selector, and if you already have a node, like let's say in your Kind cluster, you can say, hey, I want this workspace, but go to this node, and you can definitely use existing infrastructure. Yeah.
All right.
Hi there, just a curious question on Kaido. Does it provide like a way to export the chat data if you wanted to run analytics on how people are using chat, or even store that in its own database that you can run analytics on?
Kaito itself does not do that. Kaito is primarily concerned with provisioning the infrastructure for that. The way I implemented it in my sample application is I use Microsoft Agent Framework, which has hooks and the ability to export the chat metrics, chat tracing, and all that other good stuff out to Redis. So it really depends on the framework that you're going to use for your application. But yeah, Kaito will stand up the GPU and basically allow you to host your model.
Gotcha, makes sense, thanks.
Yeah, you're welcome. Any other questions? If there's no other questions, I will be at the Microsoft booth all day today, so we definitely recommend that you just drop by and have a conversation. We're actually going to be raffling off 2 Xboxes today, so that's going to be cool.
Hey, all right. I was just wondering. So if you're using like Azure AI Foundry, is there a benefit to going this route as opposed to using what AI Foundry has?
Is there a benefit of one over the other? That's really hard to say. They both do kind of the same thing. AI Foundry is more like a model as a service type method of getting your inference endpoints. Some organizations, they need everything within their network. They need everything within their cluster. And so they'll opt for a solution like Kaito to make sure that the model is running in the cluster, the app is running in the cluster, and nothing ever leaves that. So yeah.
Gotcha. All right, thank you.
You're welcome. Any other questions? Oh, yes. Here we go. Oh, sorry. Ding, ding, ding. Where is it? Where is it? Where is it? I know I had it up.
Paul, due to you.
Paul, D-O-T-U. Paul dot U. Yeah. Yeah. The actual dot wasn't available for me, so I had to spell dot.
Any other questions?
Any other questions? One last question. Okay, we have time. We have time.
All right. Yeah, I was just curious, how much of the demo slides and the code, the demo code, how much was that did you get agentic AI assistance to create all that? Like what percentage?
What percentage? I can't tell you the percentage, but a lot of I did get help from agentic AI. That is for certain. Yes. Yeah. Yeah. But you have to like steer it in the right direction, right? So yes. Yes.
Thank you, Paul. All right, thank you, everyone.
Thank you.
They won't hear you either.
Okay. Hello. Oh, that is me. Yep. You can hear me. Hello, what? Hello, Fabi. Yeah. Ah, golden.
After this talk, Fab is going to tell us how to be a golden cubestronaut in 1 month. All right, I guess we'll get started. We've got Scott and Adrian to talk about secure, scalable GPU sharing on multi-tenant Kubernetes, right?
Yeah.
So Scott Michelser, did I butcher your name? Depot, okay.
Yeah.
He's an app dev background, and he focuses on cloud native and Kubernetes, and is also an educator. Looking forward to that, educating today. Adrian, you're with HashiCorp and staff solutions architect and a former web developer. Cool, awesome. All right, we'll get started.
Awesome. Thank you. So before we get started, I need your all's help. I come from Seattle, Washington, which is up the coast from here, and I need to prove to my bosses that I didn't come to Los Angeles just for the bright, sunny sunshine, which we don't have in Seattle this time of year, by the way. So if you all could help me out, I'm going to go over here, give you a smile and wave. Adrian, turn around. There you go. Smile and wave. Awesome. Thank you so much.
Yeah, and it's even worse for me because I'm from Paris. So it was even a longer trip. So yeah, thank you all for joining us. Thank you for maybe skipping or postponing lunch for us. And let's get started.
All right, so I'm Scott McAllister, and I love to build software, but I love the interaction of software and hardware. And that's what we're going to talk about today. We're going to talk about how we can get the most out of this expensive hardware that we're all starting to use these days with GPUs, but how to get that software to interact best with that hardware. But in addition to technology and the hardware and the software, I also love cheeseburgers. Who loves cheeseburgers? And so do I. I think they're delightful. I'm also a developer advocate at a company called Depot. Depot is a build acceleration platform that essentially is a suite of tools and services that make container image builds and CI pipelines dramatically faster. We're not going to be talking about Depot for the next 60 minutes. If you want to, I'm game. We can talk about it outside. But for the next hour, we're going to be talking about these rare and expensive pieces of hardware called GPUs and how we can get the most out of those.
And I'm Adrian. I'm based in Paris. I'm a solutions architect at HashiCorp, and before that, I started my career as a web dev, then moved into SRE, so all sorts of different things. And I love broccoli. Who's with me?
Right? It's not an either or. I can love cheeseburgers and broccoli.
Right? Especially in Southern California, I'm expecting a bit more
A lot more.
enthusiasm. Come on, guys.
Yeah, more vegetation. Anyway,
Yeah.
maybe it's
Okay.
avocados. That's a California thing? Avocados? Yeah, that's what I thought. Yeah.
Okay. We can continue.
Yeah, we can agree to disagree. So why are we talking about this? That's the real question. The thing is traditional Kubernetes, right? It was built for CPUs and memory. It works best because the kernel controls everything. And so Kubernetes isolation essentially was able to use what the kernel was giving it. So in a sense, back in traditional settings, you have C groups that enforce limits, you have namespaces that create boundaries, and then RBAC controls access. These mechanisms have proven reliable for CPU and memory for decades, but with GPUs, it's different. GPUs breaks every assumption about resource isolation. There are no GPU C groups, there's no preemptible execution, no kernel visibility. The GPU driver manages everything, and then Kubernetes gets to watch from the sidelines.
And with the rise of AI use cases, I mean, like, look how many AI talks we had this past couple of days, and we'll have today and tomorrow. There is a massive growth in demand for GPUs. Everybody wants GPUs, everybody wants to do AI stuff, everybody has to do AI stuff, everybody feels left behind if they don't do GPU stuff. So yeah, we have AI interest going up. There was a recent study by Datadog they published like 2 weeks ago. They've seen GPU instance minutes go triple over less than 2 years, vastly outstripping the growth in regular instance usage. So GPU prices are also going up correspondingly. I mean, you all know this. It's pretty big issue. So that's a problem because they're often underutilized, like regular CPU and memory is often underutilized, but when GPUs cost so much, it's actually a bigger problem. Like in the same Datadog study, they found that for CPU, it's the average utilization is 25%. For memory, it's 50%. For GPUs, they didn't have the metrics, but it's probably something horrible like this. So GPUs being more expensive and less available, like it's hard to get the top-of-the-line stuff today, that's a big problem. So we need to do better for them, really. I mean, we should. So depending on your hardware, cube setup, workload types, there are a few approaches to doing this. Scott?
Right. So first, we're going to dive into MPS, or Multiple Process Service. It's the most straightforward way to share your GPUs. And I'm starting here intentionally because it requires the least from you, right? There's no new hardware, no major Kubernetes configuration. And you're essentially unlocking sharing that the GPU is already capable of. To understand why, it helps to know what normally happens without MPS. Each CUDA process creates its own context. And it creates that context on the GPU, and the driver then has to switch between them, which is similar to how a CPU context switches between threads, but with more overhead. MPS eliminates that by creating a single shared CUDA context, as you see here on the screen, where all the processes are essentially in the same pool. So they rise and fall together, which means you have the risk that if one process runs away with things and pulls things down, everybody gets to go down with it. And so there's definitely some downsides to having a shared context, but also you get speed. You get speed, and you also get speed in an easy, less friction sort of way. So enabling MPS is also straightforward. You can turn it on at the node level. And NVIDIA's device plugin stack supports it. It fits into your existing Kubernetes setup without any friction. But if you notice, as I mentioned before, for that simplicity, what are you giving up? It's isolation. If you have processes that are going to be conflicting, if you have workloads that are not trusted between different clients, that may be a problem. As I mentioned before, all the processes are in that same CUDA context, which means they sink or swim together. The memory isn't partitioned, so one process can exhaust the GPU memory and starve the others. And if a fatal CUDA error hits one process, it takes down everything sharing that same context. So for inference workloads where you can trust all the different workloads that are happening, that might not be a problem for you. But if you're in a situation where you're providing, say, hosting for multiple customers, and you have Coke on one end, you have Pepsi on the other, probably don't want to be mixing workloads between those customers. So as we move through the different strategies today, I want you to be asking yourselves, how much isolation does this approach get me, and at what cost? In this case here, MPS sits at one end of the spectrum, low cost, low isolation, but everything else we're going to be talking about is at a different point on that trade-off curve. So next we have MIG, or multi-instance GPUs, where MPS leaves memory unpartitioned and shared. MIG draws hard lines at the hardware level. It's dedicated memory and dedicated processing and dedicated compute, real isolation, so you don't have that concern that you would have with MPS. But as I mentioned, it comes at a cost because it's at the hardware level. MIG works by partitioning the GPU's physical hardware, not just the software. So each slice gets its own dedicated memory partition, its own compute engines, and its own memory bandwidth. There aren't soft guidelines that you can configure. They're actually hardware guidelines that are part of the GPU processor itself and established by NVIDIA. So NVIDIA structures the MIG partitions in two layers. First, there's the GPU instance, which is the GI. It carves out the physical resources. Then within that, you create a compute instance, which is the CI. That determines how the compute engines inside the GPU are further subdivided. So the combination of the GI and the CI give Kubernetes ultimately what it needs to make a schedulable device. For example, on an A100 80 gigabyte, you can create 7 equal slices, each with, say, what's called an 1G 10 gigabyte profile. That gives you 7 independent partitions, or 7 independent devices you can use that all have 10 gigabytes each. And you can also mix in other profiles. So if you have other workloads or processes that need more, so you say you have a 2G 20 gig profile or a 3G 40 gig profile, you can mix and match these depending on the resources that you need. However, you want to make sure that you're allocating those slices to what you need and not wasting them. In the cases where you have a process that maybe is 12 gigabytes and then you give it a 20 gigabyte profile, you're going to be wasting those 8 gigabytes. H100s follow a similar model as the A100s. However, definitely want to look into the documentation there. Even with the A100s, right? I'm only telling you a couple of the different profiles that are available. Look into that documentation that NVIDIA provides for each of those processors, but now you have an idea of what you're looking for. You're looking for profile sizes so that when you're using MIG, you can say, okay, I have these different slices and I know what type of profiles I'm working with, and then I can adapt my workloads for that. So trying to drop some like keywords and key knowledge and be like, oh right, this is what I should be looking for when I'm working with these types of processors. So because each MIG slice is fully independent device, from the OS and Kubernetes perspective, you can schedule them exactly as you would a whole GPU with the fractional resources. Your device plugin reports them as separate allocatable units, and then the pods request them by profile name, and there's no shared context or memory space to worry about. So the isolation guarantee is also stronger than anything that software can offer. A crash in one slice doesn't affect another. The memory access of one you can't access the memory of another slice. And so that makes MIG a really appropriate solution for multi-tenant environments, especially with regulated workloads where you simply can't tolerate any kind of mixing of the workloads, or at least the noisy neighbor problem that you have when you all are in that same CUDA context. The fixed partition sizes should be looked at though, because as I was alluding to before, if you have you can't create like custom profiles. Those are set by the GPU manufacturer. So if you can't say, I need 15 gigabytes. Well, if there isn't a 15 gigabyte profile, you can't just configure that for yourself. And so your workload sizes need to roughly match the profiles that you have available to you. So reconfiguring partitions it also requires taking the GPU down. When in MPS, if you're going to make changes, you can make them on the fly and keep things running for all of your users and all of your processes. But in this case with MIG, if you're going to reconfigure things and pick up different profiles and drop them, then you're actually bringing the processor down and then bringing it back up. Now, time slicing is where you have multiple workloads taking turns using the same GPU by rapidly switching access in short time intervals. So unlike MPS, where you have processes that share a single CUDA context, time slicing gives you each process its own full CUDA context, just as if it had the GPU to itself. Because in a sense, it does. It's like each process is essentially taking turns. You have our multiple processes here, and they're all lined up in nice sequential order. They all wait in line very patiently for their allocated time, and with their allocated time, they get to start, they get to stop, and they can go in order. Now, this comes at a cost because in some situation, or in every situation, every process needs to be written to memory when it's done, and then read from memory when it kicks back up. Also, if it tends to happen, if it expires in mid-computation, say if T1 wasn't quite done with its processing, but its time allotment expired, it still gets cut off in mid-computation, and then gets to wait for the full rotation of the next time T1 comes back around. That wait time might be a couple of seconds, might be a couple of minutes, it might be much, much longer than that. T1 has no control over what 2, 3, and 4 do. So it just gets to wait for that next time in line where it gets to come back around and it gets the GPU. As I was mentioning, the switching itself isn't free. So saving and restoring, as I've already talked about, to that CUDA context means that you're flushing in-flight work, you're writing state to memory, you're loading it the next context before that next work can begin. So the more processes sharing on that GPU, the more time that gets consumed by that overhead rather than actual computation or your actual work that's going on. So NVIDIA exposes time slicing through its device plugin by letting you declare a GPU as multiple logical replicas. So a single A100 configured with 4 replicas appears to Kubernetes as 4 schedulable devices. Pods request one of these logical GPUs without any awareness that they're sharing physical hardware. So the illusion is handled at the device level, or the driver level. Time slicing lands in an interesting middle position from what we were talking about before, where in MPS, each process, or it has better isolation than MPS, because each process has its own context. So a crash doesn't affect its neighbors. However, you're still sharing physical memory, just like in MPS. So there are no hard memory limits per process, and unlike MIG, the GPU isn't doing any hardware reinforcement. And so it's all coordinated in the software by the driver. There are some third-party scheduling projects that also enhance these different strategies that we have. They run on top of the strategies we've been talking about. So some of these, what they do is they don't do the sharing per se, but what they do is they add scheduling logic on top. So they add fairness, policies, priority queues, and quota management that the base Kubernetes scheduler doesn't handle well for GPU workloads. What they do is they change how the workloads get queued and assigned, and then those for those shared resources that come in. One of those projects that in particular is interesting is KaiScheduler. It's interesting because it handles something that's kind of a problem with Kubernetes in that it can only do things with GPUs in integer segments, right? It can only handle an entire GPU. Kubernetes doesn't say, I can handle half the GPU. Kubernetes is like, it's all or nothing. I can handle 1, 2, 3, or 4, or 5, all integer-based, not fractional-based. So what Kai does is Kai says, that's fine. You handle integers. I will reserve the entire GPU, and then I'll use my own annotations to say, I'll take that GPU, and then you interact, the rest of the pods will interact with that Kai scheduler, and then I can use Kai annotations to say, now I'll take a percentage or a fraction of this GPU to make it so that I can start divvying out processing and fully utilize this GPU and utilize the hardware across multiple processes and multiple tenants. So this means that you can express GPU fractions in your pod specs using Kai's annotations, and then the scheduler handles the placement logic to fit the multiple workloads onto a single GPU without Kubernetes ever really needing to understand the fractions. But here's the problem, though. So even though you have a sophisticated scheduling logic in place, look at what happens with these two tenants. I have a Kai scheduler that's running at the cluster level, and I can have tenant A that has its own cluster and tenant B that has its own cluster because we don't want to have either one messing with each other as far as noisy neighbors and taking over resources. However, tenant A is barely utilizing their GPUs. Tenant B is maxing out their GPUs, kind of wishing they had more GPU to process with. So in this situation here, KaiScheduler can only help out so much because it runs at the cluster level. How it best works out is for KaiScheduler to be part of a cluster that has as many GPU nodes associated with that cluster as possible, and then it can schedule out the workloads that are going into each of those GPUs. And it can say, okay, great, now I have access to all of the GPUs, and I can even out the distribution of the workloads and make sure that I can utilize this hardware, but also in an efficient manner. In this situation, you notice now the tenants are all in the same cluster. And the way that we're going to isolate those tenants, the most common way is through namespaces, which namespaces is a way to definitely make sure that you have isolation between the different tenants in a particular cluster. In this environment, though, each team, each workload, they get their own namespace with resource quotas, RBAC controlling what they can see and consume. And for many clusters, it works fine on paper. Tenants are logically separated and can't access each other's workloads directly. But namespace isolation is a soft boundary. It lives entirely in the Kubernetes control plane. The underlying node, the kernel, the GPU driver, those are all still shared. Which brings us back to the noisy neighbor problem. One tenant running a memory-hungry workload can create pressure that ripples across the other tenants on the same node. Even if Kubernetes thinks they're isolated, namespace boundaries are not going to stop that.
So here's where we land. We have Kai doing the smart GPU scheduling and the fractional sharing. And we have namespaces, cube namespaces that provide some logical isolation and some separation of concerns. But there is a gap between logical isolation and full actual proper isolation of physical stuff like GPUs. And not only physical stuff, also logical stuff. For instance, if we have admission controllers, operators like Kai itself, sometimes we have conflicting dependencies. Some team might need an operator in a specific version, some other team might need it in a different version, but operators are usually cluster scoped, not namespace scoped. So we can have some challenges there. So gaps like these are where things start to get complicated to manage and expensive to handle. So either in wasted resources or in conflicting, the management of the conflicting dependencies. So this is where vCluster comes in.
So vCluster, who's familiar with vCluster? Anybody use vCluster? It's a project that was created by a company called Loft Labs, open source, essentially way of providing virtual clusters inside of a Kubernetes cluster. It creates fully functional virtual Kubernetes clusters that run as workloads inside of an existing cluster. And they give each tenant their own isolated control plane without needing separate infrastructure. So each tenant has their own control plane, including an API server, their own data store, and even, oh, someone should have said something. There we go. There we go. So they get their own API server, their own data store, and the secret here is that vCluster syncer, which has that arrow going down through it. That vCluster syncer is the bridge between the host cluster, which is interacting with our GPUs, and our virtual cluster, which is what each of our tenants are using to essentially isolate themselves from the other tenants using those same GPUs. That vCluster syncer acts as the scheduler, essentially, scheduling the different workloads and the different jobs that are happening, but also it's syncing the resources in between that virtual cluster and that host cluster. You specify which resources you want to sync across the different clusters. You can say, here, we're going to set standards on that host cluster and say, we're going to use these particular resources for all the virtual clusters. And so all the virtual clusters get to essentially adopt what's going on in that host cluster. But then each virtual cluster has its own essentially environment. It is its own cluster. So they can install their own CRDs, their own resources, own custom operators, and manage their own RBAC rules without really affecting any of the other tenants or the underlying host cluster. Each virtual cluster just sees itself. It doesn't see anything outside of it, although from the management perspective, when you're managing all the clusters, you can see them at the vCluster platform level. So it's interesting how you can have an isolated environment that is isolated for the things you want, but not necessarily for all the things.
So that brings us to four, I suck at math, fundamental truths or problems, let's see. So GPU sharing only works when you understand your boundaries. And namespaces provide a lightweight approach to multi-tenancy and isolation, but they actually fall short in actual isolation, autonomy, and compliance. And problems that only become more acute when we have stuff like GPUs or conflicting operators. And if we end up creating a separate kube cluster for each team, we address the isolation part pretty damn well, but this costs us a lot in fragmentation, management overhead, and efficiency use of actual resources. So not great. And if we create multi-team clusters, it's great for efficiency, utilization, management overhead, but we lose the isolation again. So too many imperfect choices. What can we do here, Scott?
Well, for starters, we could use vCluster for real tenancy with per team control planes on shared clusters. You have strong isolation without the cluster sprawl, and then you can utilizing that large cluster that can effectively schedule the workloads across the GPUs using one of the scheduling libraries like Kai Scheduler. So vCluster bridges this gap by providing lightweight, fully isolated virtual control planes inside of a shared host cluster. It allows each team to run its own Kubernetes environment with autonomy, and then combine that with the tools we've been talking about. You combine it with the Kai scheduler and the fractional GPU support from the NVIDIA operator. vCluster enables the organization to maximize their GPU utilization while ensuring fairness and compliance. It also delivers strong isolation without the inefficiency of managing dozens of clusters that are isolated and spending the time to essentially underutilize those GPUs. Because remember, if you have those isolated clusters that are separated, they each are tied to the particular GPUs.
So now we have a team shared, but properly isolated cluster for each team. So that's a pretty good foundation part of it. What else do we need to have a proper, secure, multi-tenant setup? Keyword is secure. Enter vote. And why vote? Well, I know, I mean, it's a boring topic. Everybody loves it, right? Everybody knows security is super important, right? Okay. I hope. Okay.
Yes, the correct answer is yes.
Yeah, but it's serious topic. So yes, we are talking about GPUs and sharing GPUs and efficient utilization of resources, blah, blah, blah. But security is always important no matter what we do. GPUs don't exist in a vacuum. I mean, they're cool. I don't know if you saw at the Meta stand, they had a nice server with some NVIDIA stuff. It's cool to look at, it's cool to own, it's nice. But we use them, we pay the exorbitant prices, either from cloud providers or to buy them from NVIDIA because we need them. We want to do stuff with them. Stuff like inference or fine-tuning or training our custom models if we're really rich. Or running AI agents, doesn't matter. Whatever it is of those things that we do, we need to consider security and how we're handling stuff like secrets, brokering access to stuff, like the production database, which has personally identifiable information. All of this needs to be taken into account, needs to be designed for, and not just hard-coded credentials pushed to GitHub, something leaks, somebody does something horrible. So this is all very important stuff, unfortunately, because it's not, I mean, for some people it's fun, not necessarily the most fun, but it's important. And yeah, when running in Kube, everybody knows Kube secrets are not really that super secret, so we need something better. So that thing better is vote. Why vote? So at its core, it's an identity and secrets broker. It allows you to exchange a human or non-human identity for a vote identity, which allows you to access stuff like secrets. Those identities could be any number of things. In a Kube environment, there would be your Kube JOT token, which provides information about who you are, what service account, in what namespace, in what Kube cluster, virtual or physical Kube cluster. For a human, that would be Active Directory, LDAP. For a cloud VM, that would be AWS IAM or whatever. Doesn't really matter to vote. And once we're authenticated to vote, we get a vote identity, which allows us to exchange it for a more neutral one. Why would we want to do that? Most common example is MTLS. So this is mutual TLS. This is unique. So the client and the server provide a TLS certificate with their specific identity. They match. They're okay. They're happy. So this is great for stuff like agent-to-agent communication because each agent is uniquely identified and each other agent uniquely identifies the other agent. So it's super secure, pretty nice. But there's also SPIFFE, JOT, and etc. So that identity could be useful. But the more core part of it, let's say, is brokering access to secrets. So for instance, we can have a fine-tuning job which accesses the production database. We can have a specific small model which we train, which gets access to the S3 bucket, which contains all the images we use for training, while the non-production stuff would only get test data. And the cool part about those different types of credentials is you see the first one, it's the most boring. It's a username, password, the stuff that people keep in GitHub or KeePass, hopefully KeePass, not GitHub. But the more interesting part is the latter part. So dynamic credentials, what is this? So credentials are necessary, like for everything. We need usernames, passwords, identity tokens, whatever. But if they're static and live forever, that could be a problem, because if it's a password somebody created 50 years ago, nobody knows who has it, who has written it on a post-it, who has committed it to GitHub, who has given it to their OpenClaw. We don't know. So having credentials which are short-lived, just in time, generated for us, for specific use with a specific access, and then expire in like 24 hours or 1 hour or 10 minutes, it's pretty nice, minimizes exposure risk, and it's a good practice, let's say. With Vault, we also, like, it's a very boring thing, but when we have our credentials which are dynamic, short-lived, it's nice to know who did what, when, and why. So every action in Vault is audited, written down. This user, this kube pod requested the database credentials to access the production database. And then you can trace what happened in case of a leak. Pretty cool. So in a kube environment, this is how things look like, more or less. We have Vault, which gets us access to the secrets, like the database credentials. And we have the Vault secrets operator, which is deployed and which synchronizes the secrets that we need into kube secrets. And because they're short-lived, that's not a big of a problem, because even if it leaks, it's worth for 1 hour. So exposure risk is minimal. And the Vault secrets operator also handles rotation, like when we revoke the secret or when it expires, it will change it. And it can also redeploy the pods if that's needed, which usually with like AI jobs might not be necessary. Might be counterproductive, because you don't want your 2-week training job to be killed just to change a secret, but for an AI agent, it's necessary.
So wait, how do we handle multi-tenancy to make sure nothing gets shared by mistake? Because we don't want our emails to be deleted by OpenClaw or anything.
That never happens, right?
No, never.
So how things work in Vault? In Vault, everything is, it has a very robust ACL system, kind of like the Cube one, where deny by default, nobody gets access to anything unless we explicitly give it access to something. And with Vault Enterprise, we also get namespaces, which are logical boundary, which allows us to separate stuff, secrets, teams, groups, users, whatever. So we get a single highly available Vault deployment. We can get multiple separate isolated mini Vault environments. And the isolation is good for blast radius, because we'll never have the secret being accessible from the wrong team or wrong deployment or wrong kube cluster. But also it allows us to do cool stuff like automatic templating. Every kube cluster, every kube namespace automatically gets access to their corresponding Vault namespace, so we don't have any setup to do. Automatically, the Vault production cluster in AWS has access to the production data in AWS, and the training on developers' laptops never does get access to anything. So it's cool stuff. So this is the theory, how it works. In practice is like this. It's relatively straightforward. We deploy the operator in the namespace or in the vCluster, and then we have CRDs. The first one is pretty basic. It's just Vault's address. It's there. It's easy. Then we configure an authentication, and in this case, we're using the bottom. So we have a service account called fine-tuning, which is going to connect to Vault on the production role. And that's basically it. Once we do this, we get access to stuff in Vault. In this case, the stuff is a dynamic secret, so secret that Vault will create for us and will manage the lifecycle of. And the secret is a PostgreSQL credential. So it's going to create a PostgreSQL username password, and it's going to manage it for us. And the same CRD works also for cloud credentials, for PKI certificates, for MySQL databases, for MongoDB, and for a bunch of other stuff. Pretty much everything we could want. And this only works if we actually have access to that PostgreSQL credential. We don't give it to everybody, of course. So how it looks like is we have to create a row in Vault, which just says which service account from Kube and from which namespace is allowed to access that thing. And that thing is the PostgreSQL credential. And that's it. It's relatively straightforward to give specific isolated accesses to specific isolated things based on what they actually need.
So remember, vCluster gives us real tenancy and isolation, but now we layer this multi-tenant service. So we have Vault for secrets, and then GPU sharing or scheduling with the NVIDIA operator, the scheduling with the operator plus Kai, and then we turn that foundation into a secure and fair, efficient platform.
So a couple of notes to finish off with good things to remember. So complex systems fail. Everybody knows this. So there is no excuse not to build with complexity and failure in mind. Everything will break no matter how hard you do it, no matter what your foundations are, something is going to break at some point. So the difference between a good and a great platform or SRE or DevOps or whatever you call them team is having playbooks and having planned for this kind of stuff. And part of architecting for failure is architecting for isolation. You don't want one team's failure or one application's failure to impact everybody and everything. And isolation only works because it adds extra defensive layers. More layers equals more protection. More protection is good.
Building on what Adrian was saying, defense doesn't just come from the outside, right? For incidents, it also comes from the inside. vCluster actually has virtual clusters that help you contain that blast radius. So if something goes wrong in a particular virtual cluster, say a bad commit or a misconfiguration, it doesn't get proliferated across everyone using that same host cluster, right? Each virtual cluster gets those isolated so you can have that defense and limit that blast radius. Also, vCluster gives us a couple of different audit layers or audit options. Essentially, at the tenant layer, every virtual cluster has its own API server, so it has its own API server logging that's available in every Kubernetes cluster. And so you can have all the different logging that happens there, but then at the platform level, you can have logging that essentially tells you what's going on in each of your clusters, who's creating them, who's modifying them, but also making sure that they all are running well together, giving you that data so that you can make those decisions. I used to say you can take that data and export it into something like Datadog for you to look at and analyze, but now what are we doing, right? We're taking those logs and we're giving them to agents, and then we're having those agents decide what's going on and help us make decisions with our applications, which in some cases works well for us, or for all developers. So we appreciate you all coming in here today, especially since we are the thing that's holding you from going and finding lunch. So we appreciate your attention. Please, if you'd like to see the slide deck, font should be bigger, speakerdeck.com/stmcallister. Otherwise, we have a couple of minutes for questions.
Thanks, great presentation.
Thank you.
Sorry, might be a naive question, but I didn't you said namespace, when you do namespace with Kai scheduler, just logical isolation, I understand that. But how is vCluster solving that problem? Because that is also logical isolation only, right?
What vCluster is doing is, in addition to the namespaces, you put Kai scheduler on that host cluster, and then vCluster is the thing that's keeping each of your tenants isolated from each other. So you're basically giving stronger walls than just what namespaces were providing to each of the tenants that are sharing those virtual clusters.
Okay, but that's also at the logical level only, right?
Mm-hmm. So like I said, namespaces can happen. You can make it work, and you can configure it. What vCluster is doing is it's essentially making that easier for you to do, right? Without you having to keep all the different permissions and things separated and keeping those managed as well.
Okay, got it. And then you had another point saying it might be a problem for operator because they're cluster scoped. You can have operators run in CPUs instead of GPUs, right? Because operators are not going to be typically CPU intensive.
Right, so operators can run, the question was you can have operators running, again, CPUs and with GPUs because they're not scoped to particular processors. Operators are generally scoped at the cluster level, right? So that if you have an operator that is benefiting the entire host cluster, then yeah, then you would put those operators there in that host cluster. If you have an operator that's specific for a specific tenant, then you would want to have that operator running in the virtual cluster. Mm-hmm.
Any other questions?
Great presentation.
Thank you.
I'm wondering how dynamic can like the scheduling be, where like if I have a GPU or I have a process that's being used for inference, so I'm hosting like a large model that's using multiple GPUs, and then I also have another team that wants to run experiments and train their own model, but they don't really need to have the whole GPU. Is there something where you can like temporarily pause some one of the instances of like not allow inference for a little bit, or if someone then wants to put in a request for inference to like pause at a step of training?
So the question was, yeah, can you essentially dynamically decide if it's being utilized, can I spin something down, and then if you have a large workload come in, can I dynamically spread it out? Kind of like in my head, thinking of like how like hypervisors work, like right, like with EC2 or something, where it's basically saying you spin up servers when you need them, spin them down when you don't. That type of questioning. I'm not an expert as far as exact specifications of the different scheduling pieces that I was talking about. But as far as like using them, as what they do is like something like Kai Scheduler makes it possible to do that. It makes it possible to provide fractional portions of those processors. But how you would dynamically, like, could you send that like configuration of saying, hey, we're going to use 0.2 of this GPU, and then like, wait, this is getting bigger. Now I need to use 0.75 of this thing, or 1 or 2 of these things. I don't know how you would do. I don't know how to do that. It's like if that's built into the scheduler itself, or if that's something you'd have to kind of put logic around in your configurations. Maybe using something like Carpenter, something like that.
Yeah, thank you.
Oh, you don't have the mic. You're saying Kai has priority based into it. So yeah, you know a little bit more about Kai than I do on that particular piece.
Yeah, sorry, just wanted to say that yeah, Kai has you can configure priorities in Kai. I don't know if you can tell it to evict a lower priority workload or pause it or something, but in any case, yeah, they have priorities, so probably that's why they are there. But yeah, that would be something to check out.
Thank you. Sorry.
Thank you for your presentation. I'm kind of behind, so what, not the namespace, but the other one, what's the name of that? I can't remember.
vCluster?
Yeah, so what if the vCluster fails or dies, what happened? Because, you know, things do fail, so does it mean another one comes up?
As Adrian mentioned, right? We should always architect for failure.
Yeah, so
everything
is
breaks.
that what it does?
So in the case here, are you asking if vCluster as a tool? So
Yeah.
if one of the vClusters falls over, can I spin up another one?
Yeah.
I mean, essentially, yeah. There's a vCluster employee right there, so he knows specifically. But yes, they definitely spin back up. They're just like any Kubernetes resource, which is one of the great things about Kubernetes.
Right.
It makes it possible so that my resources are going to be running, and if they need to be restarted, it'll restart them for me. Those types of things. So yeah, vCluster will restart their virtual clusters when they need to.
Okay, thank you.
Yeah.
That's great, because, you know, as a cybersecurity professional, I'm always thinking about if something fails. Now, I
Right.
do want to ask you about, again, I'm behind, how does this vault dynamic secret, I assume that's from HashiCorp. Is that right? How does that really work, the dynamic secret thing? Can you explain a little bit?
Oh, yeah, grab, okay. I thought I'd be replaced.
Thank you. So yeah, it's Vault from HashiCorp, and the way it works is you give Vault access to manage credentials in a database. So for PostgreSQL, you need to give it kind of an admin account. And then when you request read-only user for the production database, Vault will connect to the PostgreSQL, create the account with the specific grant, and give you the credentials for it. And with a specific time to live, so like 1 hour or 24 or whatever is configured. And when they expire, Vault is going to connect to delete it. So even if you still have it, it no longer works. And that's the same logic used for AWS, Elasticsearch, MongoDB. Yeah, it's with the DTL which Vault manages itself, and Vault will delete for you, so you don't, even if you just run a test, you don't have to care about deleting the credential afterwards.
And then I will say about the comment that you're behind. I wouldn't say anyone's behind, right? No one knows all the things about all the things. That's why we're at conferences, right? That's why everyone's here is like, I'm trying to come see what people are talking about. So I think having the courage to ask the questions is exactly the type of mindset you need to have to learn. So well done.
Does vCluster have its own secrets management? Why wouldn't, or not? I mean, do you have to use Vault, or can you use vCluster?
So vCluster is just it provides the engine for you to create virtual control planes. So any Kubernetes cluster, so if like a Kubernetes cluster needs to have a secrets manager part of it, or you can use secrets inside of that Kubernetes cluster, right? Like you can use secret objects in there. So if whatever you use inside of a regular Kubernetes cluster, you can use inside of vCluster as well. So it's essentially the same thing. It's just providing it on a much more finite level.
And I think one of the things that she brought was like there could be failures, but that could be control plane failure or an agent, right? But if the control plane is off, the agents are.
Yeah, so basically if the control plane dies, everything is running. And depending upon how you are storing your data, the control plane picks up again. But everything will keep on running till your control plane is not going, because the architecture is as such that your API server is running as a pod. So if the pod fails, it can be spin back up, but your workloads are running. Yeah.
Please.
So I have this question. So the thing dies and this thing comes up, vCluster. So it's great, right? Magic. I mean, I like it. But are we losing any kind of data, or how does this sync up? Have always been a mystery to me. People say, well, it just comes up. And so there's nothing lost in the transit. This kind of thing, is it backup? You're doing a sync all the time to make sure everything is.
So data itself isn't like that's getting into the scope of talking about Kubernetes as a concept itself. Data itself is going to be saved into things like persistent volumes, right? Or stateful sets, right? And so those you want to be saved, but you'll be syncing those things as well.
And to add, like whenever you are creating or doing any objects, so the step how it works is when you create, first the data store is saved in etcd, and then things are created. So the source of truth is there. So it's not the other way around. So it keeps on syncing between the API server and etcd. So that's the truth state.
And then you can, if you're thinking about the etcd failure, you can design your control plane in a manner that you never have that issue either.
Yep. Right.
Any other questions? Of course.
Here we go.
You better watch out. This guy's a golden coops or not.
Yeah.
Just so you know.
Yeah.
Not a bad one, but I heard something about Vault that I'm curious to know, because immediately triggered me in my brain the hacker mind. So you said that Vault is going to connect to the database and delete that credential. When you did the presentation, I was thinking that the credential was going to expire somehow. So if Vault has to go there and delete the credential, and I impede that, creating a network policy, an example on the cluster, and avoiding Vault to connect to that database, and I steal that credential, will there be a way, a better one, for Vault to be managing these credentials with an agent or something that is effectively running inside Kubernetes? Because I know that Vault has an agent also, and you can use that. So I'm curious about that process that you mentioned. Vault is going to connect to the database. Could you give me a little bit more details on what you do there?
Okay, thank you. So yeah, it's Vault, the servers that have to connect to the database to be able to delete the credentials. And indeed, if you've cut the network access from Vault to the database, it would not be able to do so. It will keep retrying, and it will keep a list of all credentials it did not already delete that it should have, so it will keep retrying forever. But yeah, it needs direct access, and this is only handled at the Vault control plane level. You cannot use the agent for that. It's because it's so the control plane is a distributed cluster like Kube itself, so all the decisions are there because it ensures good reliability and fault tolerance and etc. So yeah, not really.
What are the key differences between storing the credentials as well we talked about earlier in a Git versus Vault?
Okay, so if you store the credentials into Git, they are forever there in the commit history. So you always, like even if you say to yourself, oh, actually that was a bad idea, I'm going to remove them, they're still going to remain there in the history. I mean, you could remove them, but it's really not easy. And the thing is that usually a lot of people have access to Git. So for instance, all developers working on a repository will have access to the repository. So they will be able to see all the secrets. They'll be able to copy those secrets, like to their laptop, to run a test or a dev environment. So you lose control, you lose any even knowledge of who has those secrets, why, and who has used them when and why. And yeah, everybody who has access to the code will have access to the credentials, which, especially in a production environment, you don't really want that. Yeah, you trust your developers to write code, but you wouldn't trust them necessarily to have access to the production database. And this is not just developers, like there was an example we were talking about yesterday. Some guy was complaining that he was using code to write, to update the version of the website, and Claude deleted all of his environment using Terraform, just run a Terraform destroy, auto approve. So deleted the database, deleted the backups, etc. And it's not a Claude problem, you just gave it too much access, and it's the same logic. You give only the necessary access, so a developer, they don't need access to the production database. Claude does not need access to your production database. So it's separation of concerns and knowing who has access to what. And in Vault, all the secrets are encrypted, which is also nice, but also you have the very good RBAC, so only the things that you've authorized to access those secrets have them. And you know who accessed them, so yeah. Basically, Vault is better for the big team, is what you said. Yes, but even for small teams, you need something better than Git. Even GitHub secrets is better than just putting them in Git. So for a small team, good question. Usually, most platforms already have something planned. Like for instance, if you're running on AWS, they'll have AWS Secrets Manager. If you're running on Vercel, they have a secrets thing. So look at what the platform provides, look if it fits your needs, and use that if it works. You're welcome.
Back to her. I just wanted to say, as a cybersecurity professional, we do not recommend you put anything past your secret in Git repository, because we heard attackers are going over, they're able to see those kind of things. So definitely Vault is the thing. I'm not saying it has to be HashiCorp Vault. I'm not. Just it has to be in Vault. If this is something really important, because I've heard so many stories, they're looking at people's credentials in the Git repository. Not to say if you don't set up correctly, people can just go there and get it. Yeah, just a comment for you because we hear that over and over again.
Thank you.
Thank you, everyone.
All right. Is that it? Awesome. Thank you all for coming. Enjoy the rest of the conference. Thank you.
Platform engineering for LA as well.
Test, test. Yep.
So that's Luca and
Test. Test. Hi everyone, I hope you guys are all ready for our talk today. I just want to warn everyone that there will be QR codes in this presentation, so make sure you have your devices ready. All right, let's start off with some introductions. My name is Angelica Ambrosio, and I am a DevRel engineer at U.com. I have a background in platform engineering and teaching. I specialize in DevOps and AI, and my hobbies are breaking down buzzword-heavy topics and complex tech concepts into ideas that engineers can actually use. And with me, I have...
Test. There we go. Christian Hernandez from Cisco on the Isovalent team. I am background is platform engineering, DevOps. Kind of I used to call myself a Linux command line samurai. So for the past, 10-ish years, I've been really into cloud native Kubernetes. I am a contributor to the Argo project. I am a contributor to Open GitOps. I am an LA native. It took me an hour and a half to get here, so that's how I'm an LA native. I always joke that I can fly to San Francisco, get there quicker than I can to this conference. So that's a little bit about me.
All right, before we dive right in, I want to give a little bit of background on U.com and the team behind it. So U.com has been driving major advances in AI and search long before the current generative AI wave. So our founders, Richard and Brian, have been pushing the frontier of AI, natural language processing, and LLMs for more than a decade. Long before the current wave of generative AI, their research at Stanford helped pioneer deep learning approaches to NLP, including work that leveraged NVIDIA GPUs to scale neural networks for language understanding. Over the years, this work helped drive major breakthroughs in contextual language understanding and search, fundamentally changing how machines process and retrieve information. So at U.com, we've continued pushing that boundary. We're among the first to actually fully connect large language models to the live web, enabling AI systems to access real-time knowledge instead of relying solely on static training data. Now we've continued building innovations around AI-powered search and deeply personalized AI experiences, all supported by a full web API that developers can integrate directly into their applications. So at U.com, we work with many of the world's leading AI teams, and our APIs are built to handle massive global traffic. Today, we're serving over 1 billion queries every month, supporting thousands of API customers globally, and we're seeing strong adoption across the enterprise, including over half of the Fortune 500. And that's the experience we bring to the space. So today, I'm going to show you how you can build AI applications more smoothly and securely with Cisco.
Yeah, so just a little bit of background about Isovalent. So Cisco acquired Isovalent maybe about a little over a year ago. And Isovalent was really focused on networking and security in a cloud-native ecosystem. So basically taking all the network security aspects that normal network operation folks care about and bringing those to Kubernetes, because let's face it, just because you're moving your workloads into Kubernetes doesn't mean your old security practices doesn't also apply there. So that's kind of like the idea around Isovalent and all the tools that Isovalent built in the open source ecosystem. And now we're part of Cisco and basically became that kind of cloud native OSS branch of Cisco. So go ahead, next slide. Yep.
All right, so now that you know a little bit about us experts, we're going to tell you about the agenda for today. So we're going to talk about the rise of AI, why AI is breaking traditional infrastructure, 3 common mistakes with AI infrastructure, how to build the right foundation for AI workloads, how to enforce security and compliance, how to add live data to your AI, and then we'll do a high-level overview, how this benefits you, and we're going to close everything off. So let's talk first about the rise of AI. AI adoption is accelerating, but infrastructure readiness is lagging behind. So you want to adopt AI. As more enterprises adopt AI, they quickly learn that traditional infra isn't cutting it anymore. Your infrastructure needs to evolve in order to handle AI. AI workloads demand new approaches to compute, storage, and security. Many make the mistake of neglecting their infrastructure needs by blindly developing infrastructure without a proper strategy. So here are a couple of challenges that can arise without proper strategy. Number one, the VM mindset. When teams think about AI infrastructure the same way they think about traditional workloads, they often fall into what we call the VM mindset, spinning up virtual machines and treating those resources as fixed units. The challenge is that AI workloads are fundamentally different, so VMs can be too rigid and inefficient. Two, GPUs. Okay, let's be honest, GPUs are really expensive. Over-provisioning GPUs are poor return on investment, having idle GPUs just sitting there consuming power and budget. And then lastly, traditional infrastructure security often assumes isolated services and predictable traffic, which works fine for most enterprise apps, but AI workloads are built different. They're constantly moving data between the nodes. And then now Christian's gonna talk about why AI breaks traditional infrastructure.
Yeah, so as AI workloads are landing onto to our environments, there's some challenges that come with that, right? So like basically the extreme GPU demand, right? So as Angelica said, GPUs not only expensive, but they also like cost in terms of like your environment, right? To the actual physical hardware. And all of a sudden, high performance networking is important, right? So all of it, you know, now you're measuring IOPS and things like that. Whereas maybe before, if you weren't doing AI workloads, maybe you weren't so concerned about like some of these things, right? Also, security and compliance needs, right? Those never go away. You know, even if you're running like, you know, the newest of the new, the coolest of the cool, the latest things, right? And right now, AI is the hot topic. So, but those compliance and securities, that stuff never goes away. And AI workloads will, you know, often exceed VM design limits, right? You design over a certain workload, now you're trying to shoehorn in this newer workload into a system that may be designed for something else.
All right, have you ever wondered what goes on under the hood of generative AI? I have on screen a diagram of the architecture of a typical generative AI system. I like to think of it as 5 core layers, starting from the bottom and moving up the stack. So think of it like as a big cake of AI. So at the very bottom, we have the data layer. This includes all the structured and unstructured data used to train, fine-tune, or ground models. For most AI systems today, this could be documents, logs, databases, or internal knowledge bases. The quality, governance, and accessibility of this data directly impacts model performance, so keep this in mind. Above that, we have the infrastructure layer. This is where the compute lives, your GPUs, Kubernetes clusters, networking, storage, and your orchestration. This layer is responsible for scaling, training, and inference efficiently across environments like cloud, on-prem, or the edge. And above that, we have our LLM layer, which is the core intelligence of the system. Think of it as the brain behind the operation. This includes things such as foundation models, fine-tune models, and inference services. This layer handles reasoning, generation, summarization, or any other AI-driven capability. On top of your models, you would have your middleware and your API layer. This layer connects models to the rest of the system. It includes things such as the orchestration frameworks, RAG pipelines, vector databases, prompt routing, and API gateways. Essentially, this is the glue that allows applications to reliably interact with their AI models. Finally, at the top of our cake is the application layer. This is what users actually interact with: chatbots, search interfaces, automation tools, or enterprise applications powered by AI. And then we have on the right the several cross-cutting pillars that make the architecture production ready. We have LLM Ops, which covers monitoring models, managing deployments, versioning, and evaluating performance. Second is user feedback capture, which is critical for improving models over time. Third, we have security, which is very important, which includes protecting sensitive data, controlling model access, and ensuring safe interactions. Finally, responsible AI, which focuses on governance, transparency, and compliance. Together, these layers and pillars form the foundation for building effective, scalable, secure, and production-ready generative AI systems. And today, Christian and I are going to talk about open source software that can serve as a starter kit to create the infrastructure or the foundation of your generative AI system. That means you can create the next ChatGPT with this. But first, let's cover what not to do when developing infrastructure for AI.
So we're going to go over like the 3 common mistakes that folks make. This is kind of just generic things that we see out there when going into when you're first stepping into creating a AI infrastructure or an infrastructure ready for AI.
All right, so from what we've seen working with teams building out their AI platforms, there are 3 really common mistakes that come up again and again. And here we're going to learn from their mistakes. The first is over-provisioning resources. Since AI workloads require a lot of compute, like GPUs, it can make teams a little nervous about running out. So this leads to GPU hoarding. And the result is clusters full of idle GPUs. Instead of dynamic scaling and efficient scheduling, you end up with large amounts of unused resources. And then the second mistake is a legacy infrastructure mindset. So think back when I was talking about the VM mindset. It's the same thing. Infrastructure isn't one size fits all. When teams try to run modern AI workloads on top of traditional infrastructure, things are going to break down. You get poor alignment with Kubernetes native patterns, limited flexibility for training and inference workloads, and infrastructure that simply wasn't designed for the scale or complexity that AI requires. And then lastly, Christian will talk about security.
Yeah, so insufficient security, right, I think is probably one of the things. And we'll go over it a little deeper as we progress here. But data leaks, right? Like in terms of data, that's just always a thing you need to think about and take care of, regardless of what workloads. But now when you're thinking about like sensitive information, people using AI to assist them in, I don't know, running reports for customer spend, right? You're seeing sensitive data, and you're seeing these AI leaks that can happen where, all of a sudden they have customer information or sensitive internal information. And network security is always going to be something regardless of the workload, but especially in AI when different things, you're saying things about like OpenClaw and things like that, being able to access different resources. Network security actually even becomes even more important in terms of AI.
You don't know how many times we've seen people putting in customer like credit card numbers and phone numbers into ChatGPT. This is really important. All right, so let's talk about building the right foundation. So infrastructure is foundation. So think of it like you're building a house. You want a strong, sturdy foundation because you don't want your house to collapse, right? Or think of it as a big bridge. And this bridge needs to handle like 100-pound, 200-pound big rigs going through. That big rig is AI workloads. They're huge, they're resource heavy, so we need to have a foundation that can actually handle it. So I recommend using Kubernetes for your infrastructure. Kubernetes is actually a really good solution for creating AI infrastructure, despite not originally being created for AI. Scalable distributed workload orchestration is one big perk. AI workloads, especially like training jobs, often need to run across multiple nodes and GPUs. Kubernetes can make it easier to orchestrate these distributed workloads, schedule jobs across clusters, and manage them reliably at scale. And another good benefit is the efficient GPU resource scheduling. GPUs are one of the most expensive resources in an AI environment. Kubernetes allows you to schedule and allocate GPUs across workloads so teams can share infrastructure more efficiently instead of dedicating hardware to individual products. So that's like saying, I'm going to have a GPU for this, I'm going to have a GPU for that. No, you don't want to do that. 3, automated deployment and scaling. AI services like model inference APIs often experience fluctuating demand. But Kubernetes can automatically deploy, scale, and manage those services so applications can handle that spike in traffic without manual intervention. 4, cloud-native infrastructure flexibility. That means that you can run AI workloads across cloud, on-prem, or hybrid environments. That flexibility is super important because many AI systems involve huge data sets, specialized hardware, or regulatory constraints that require infrastructure choices beyond just one cloud provider. But even though Kubernetes wasn't originally built for AI, its ability to orchestrate compute, automate infrastructure, and scale workloads makes it one of the most powerful foundations for running AI systems in production. But can Kubernetes stand on its own? So, can I just start creating infrastructure for the next ChatGPT with Kubernetes alone? No. It was originally designed to run stateless web applications and microservices, not AI workloads. Because of that, a few challenges appear when you try to run AI systems directly on vanilla Kubernetes. Because GPU scheduling isn't optimized by default. Kubernetes can allocate your GPUs, but it doesn't naturally understand AI workload patterns like GPU sharing, memory constraints, or scheduling long-running training jobs efficiently. That could lead to fragmented GPUs or idle resources. Second, AI workloads are often long-running and stateful. Training jobs, fine-tuning pipelines, and data pre-processing tasks may run for hours or even days and require checkpointing, distributed coordination, and fault tolerance. Kubernetes was primarily designed for short-lived stateless services, so additional tooling is needed. Third, AI pipelines are complex workflows. Model training, evaluation, fine-tuning, and deployment are multi-step processes involving data pipelines, distributed training, and model versioning. Kubernetes itself doesn't provide native orchestration for machine learning workflows or experiment tracking. 4, data movement becomes your bottleneck. AI workloads move huge amounts of data between storage systems, GPUs, and pipelines. Kubernetes doesn't automatically optimize high-throughput data pipelines or distributed training communication. And then finally, this one's a little more obvious. Observability and cost control become difficult. GPU clusters, expensive, and without specialized monitoring, it's difficult to track GPU utilization, model performance, and cost efficiency across AI workloads. But the good news is this can be optimized by adding the right management and automation layer. And that's exactly where Cordant comes in. Introducing Cordant. So Cordant is an open source Kubernetes native platform by Mirantis. It centralizes the management of your Kubernetes clusters across the cloud, on-prem, or an edge. It has declarative GitOps-based automation for infrastructure and workloads, meaning that you can start streamlining cluster provisioning using templates. You can start streamlining your service deployments using a template. You have built-in policy enforcement, governance, and lifecycle management. And it's designed specifically for these modern distributed and AI workloads. And the cherry on top, you get Cordant Observability and FinOps, aka COF, not King of Fighters, for visibility into cost and resource usage. So let's take a look at exactly what COF does. COF is an observability and cost management layer built for environments running their Kubernetes-based infra, especially those supporting distributed and AI workloads. When organizations start running Kubernetes at scale, especially for AI, they usually end up stitching together a whole stack of tools for metrics, logs, tracing, you name it. This is what we call tool chain bloat. Each of these tools have its own config, upgrades, and operational complexity. What COF does is just simplify that whole stack. It bundles all your observability and cost management tools into a single subsystem that can be deployed consistently across all of your Kubernetes clusters. And it's all managed by a single control plane. All your favorite observability tools bundled in one, such as Grafana, Victoria Metrics, OpenTelemetry, without the cost of managing them all individually. And from an observability perspective, this collects metrics, logs, and traces from every cluster in your environment. That means platform teams can monitor their performance, troubleshoot issues, and understand system behavior across their entire infrastructure. Now, at the same time, COF integrates FinOps capabilities using tools like OpenCost. This connects infrastructure usage directly to cost data, allowing teams to see exactly which workloads, namespaces, or projects are driving their spending. So we have here up on screen, this is Coffee with Grafana. So all of your favorite observability tools are already included. You can use whatever you'd like. AI infrastructure is typically built around expensive resources like GPUs and large-scale storage. Training jobs, inference pipelines, and data processing workloads can run for long periods of time and consume massive compute resources. Without the proper visibility, your organizations are going to end up with idle GPUs, over-provisioned clusters, or runaway infrastructure costs. Another advantage is consistency across their clusters. Instead of building and maintaining observability stacks separately for each environment, COF ensures that every cluster deployed with Cordant automatically includes the same monitoring, tracing, logging, and cost tracking capabilities. So instead of spending all your time integrating tools, troubleshooting version mismatches, or building cross-cluster dashboards, Platform teams get the standardized lifecycle managed observability and FinOps platform from day one. The TLDR, COF gives organizations visibility into both performance and costs, which is critical when operating large-scale, GPU-heavy AI infrastructure. So, I know I shared a lot about Cordant, so let's summarize. Why is Cordant optimal for AI infrastructure? Cordant effectively makes developing AI infrastructure with Kubernetes an automated, lightweight, smoother process. Your MLOps, LLOps can become super simple and composable, and here's why. Number one, resource efficiency and GPU utilization are improved significantly. Instead of manually managing your clusters and risking idle GPUs, Cordant orchestrates all your Kubernetes environments across cloud, on-prem, and edge. Second, AI infrastructure becomes declarative and automated. So that means that we use GitOps-based workflows. Teams can manage their clusters, workloads, and infrastructure configs in a consistent way. That means training pipelines, inference environments, and supporting services can be deployed and updated reliably across environments. Third, distributed AI environments become easy to operate. That means AI workloads often span multiple clusters or environments. Cordant provides that centralized management across these clusters, which simplifies running large-scale training jobs or inference systems without managing each cluster individually. Fourth, platform consistency improves across teams. Instead of every team configuring Kubernetes differently, Cordant provides standardized templates, policies, and lifecycle management. This ensures AI platforms are reproducible, scalable, and easier to maintain. And finally, observability and cost visibility through Cordant Observability and FinOps, aka COF. This provides insight into resource consumption, infrastructure health, and GPU usage, and it helps orgs understand where resources are being spent and optimize their AI infrastructure. So effectively, Cordant turns Kubernetes into a manageable, scalable orchestration platform for running those distributed AI workloads. So I really like COF because it bundles all of my favorite observability tools into one, and I can manage them all from a single point of control. But I'm going to be honest, I like to use a lot of tools when it comes to Kubernetes. But this can be out of control quickly, and I end up with tool chain bloat. How many of you do the same thing, where you just got to get like 50 different tools just for one project? Exactly. For those of you who can relate, you're going to love this. One huge benefit of using Cordant is the curated Cordant catalog. You can create multi-services, which are bundles of your favorite tools, and bootstrap them to your clusters via service templates. The catalog is very extensive and makes it easier to strap on all your favorite tools without the additional overhead. If you look up the Cordant catalog, you can see the full list. And wait, what's that over there? Oh, okay. We're going to learn from Christian what Cilium is.
Yeah, I have this here. So, I'm going to talk about enforcing security and compliance with Cilium. So, basically, how to keep your data safe and compliant with Cilium, and how you can use it in the age of AI. So, before I get to like the security aspect in enforcing, I'm going to talk a little bit about like what is Cilium. So for those who aren't familiar with Cilium, I hope you're at least familiar with Kubernetes, is that when I say Cilium, or when people talk about Cilium, it's actually talking about a few different things, right? A few different tool sets. With Cilium, right, it's all under the Cilium open source project, right? It all falls under that. But usually when someone says Cilium, you think about Kubernetes networking, you think about the CNI, right? Because at its core, that's what Cilium is, right? It implements the container native interface for Kubernetes, right? To basically provide that flat network that you do when you first deploy Kubernetes, right? But I always like to say Cilium is a superset, meaning that yes, it does implement everything that the CNI does, things like network policies and all of that, everything that kind of like what you would used to be using, but more, right? Because Cilium also gives you things like IPsec, you can do things like BGP, you can do things like IPAM, egress gateway, things like that. When you're doing network policies, we actually go beyond layer 3 and layer 4, right? You can go all the way up to layer 7. and even do things like DNS, which I'm going to show in the next few slides here. Then with all of that, everything that Cilium gets you, for those folks that are like network operation folks, everything that Cilium gets you, you also get what I call the batteries included observability platform with Cilium, which is you can use Hubble, right? We call it Hubble Timescape. You can use Hubble, or you can plug in things like Grafana, FluentBit, things like that, right? As well, right? You don't have to use the Hubble CLI. And then also service mesh, right? So basically anything that's ingress, gateway API. So if you think about it, everything from when traffic enters your cluster all the way down to the actual pod, to the workload, Cilium takes care of all of it. And then there's this tool called Tetragon. So Tetragon is based on, and so is Cilium, but Tetragon is based on eBPF. So for those unfamiliar with eBPF, I can actually do a whole 2-hour presentation on eBPF. But in kind of a nutshell, you write these, I guess, kernel programs that execute on runtime that you can set certain policies on. So when, let's say, someone tries to write a file or read a file off the operating system, you can set policies around who's allowed or what kind of workload is allowed to do that, and either block it or mitigate it somehow. So, so if you think about like this whole platform as like a kind of a whole thing, from when the traffic enters your Kubernetes clusters to all the way down to when the disk action happens, when stuff happens in the kernel, you can manage all of that using Cilium and Tetragon. So Cilium in a nutshell, Tetragon in a nutshell. If there's other talks around there around Cilium and Tetragon, or eBPF, I encourage you to go attend those talks. Because now I'm going to talk about how can we secure AI systems against evolving threats. So the MIT RE Adversarial Threat Landscape for Artificial Intelligence Systems, that is a mouthful to say, so I'm just going to call it ATLAS. So the ATLAS framework is a knowledge base that documents tactics, techniques, procedures used against machine learning systems. And it helps security teams understand how ML models can be targeted, how you assess vulnerabilities, develop defenses. So Atlas is modeled after, another mouthful, MIT RE, Adversarial Tactics, Techniques, and Common Knowledge, or ATTACK. So it's modeled after that, but focused on AI ML workloads. So these are kind of some of the examples I'm going to go through in the next few slides. And if the demo gods are with me, I will show a demo. So everyone pray to the demo gods.
Pray to the demo gods.
Yes, exactly. So one of them is a backdoor ML model, right? So, and another one is ML supply chain compromise. And another one is a data model poisoning. So we'll go in deeper what it is in the next few slides here. There's another thing out there, the Open Worldwide Application Security Project, or OWASP. So with OWASP and Atlas, they maintain a list of the most critical security risk in LLM applications. Every year, OWASP does a top 10 of basically what's the top 10 kind of like most things that can happen, and mitigation measures as well. So as you know, working with LLMs becoming more and more popular, it's important to keep kind of up to date with all of this stuff and like, you know, kind of have a framework. So you have kind of have a cool framework of using these tools together, Atlas and OWASP, and you know, it's kind of like a good way forward here. So there's 3 things, right, that kind of relate to the prompt injection, right? Is kind of like, you know, these out of the top 10 of this, I picked these 3 out because it relates to the other 3. But prompt injection, right? So this is Hugging Face Poison GPT attack, which was theoretical, right? But they actually did prove it out in a lab where they show that it was possible. Supply chain attack, right? PyTorch, this is something that actually did happen. And basically, as Python is becoming more and more popular because of AI ML workloads, PyTorch it kind of showed this vulnerability showed the fact that you can import vulnerabilities, right? I guess like for those that are into security, these are what we call transitive things that happen, right? Transitive vulnerabilities is like, oh, like maybe your software isn't vulnerable, but you imported something that was. And then there's data and model poisoning, right? This is what Pramalama was all about, was basically file tampering. And so paired together, right, with the OWASP, you pair it together with Atlas, you kind of have a good like foundation and framework to help you, right, to secure the platform for like getting ready for AI ML workloads. So, so I'm going to go through kind of how like each one of these examples and how you could have mitigated that or how you can mitigate that with Cilium or Tetragon. The first one was the ML supply chain compromise, right? So this one was, the example was the PyTorch example, and basically, someone imported something they shouldn't have, or something that was compromised somehow. So really around this is that this is kind of this is very, very tiny. So I probably should have made it bigger, but this is a network policy, a Cilium network policy. Again, I say it's a superset because this actually filters out based on FQDN, right? So if you think about like Kubernetes and like IP addresses and those that are from like a more traditional networking standpoint, like the IP address, right, is like the canonical thing, whereas Cilium takes care of things in terms of like identity-based model, where it's like, okay, like doesn't matter what the IP is, I am going to filter based on DNS name, right? And so you can filter based on DNS name, basically internal or external, saying, hey, I'm not going to allow any workloads to import anything other than like maybe a trusted repository, right? Maybe you have Artifactory or something internally that you scan regularly and you trust, and you don't want developers pulling things from the internet or anything like that. You can like filter out based on DNS, right? And so, so that's kind of like what you get with Cilium, right, out of the box, right? Open source, you go and you be able to set some of these policies. So that's one way Cilium helps. The next one is the backdoor ML model, right? Which this is the eBPF-based thing that I was telling you about Tetragon, where basically this is based on the Poison GPT attack, right? Where you have a manipulation of training data to insert like hidden triggers, right? Like if someone says, oh, hey, help me with this customer, and then all of a sudden that triggers something like, oh, anytime someone mentions a customer or like inputs like some sort of data, email me that data, right? So like they insert like hidden triggers there as well. So again, this here, if for those in the front, those in the back, I apologize, but in the front you can say, oh, hey, don't allow this system call, right, to happen to this file system, right? Don't let it read this file, or don't let it execute things. Anytime someone reads a file, don't let it execute anything else, right? And so this is kind of like how it can help to mitigate that, right? And this one is kind of cool. This is kind of my favorite, and this is, again, hopefully one I can demo, is that the attack vector is basically you manipulate model behavior. You basically saying, let it give the person using the model false information. And so malicious false information. So, and again, you can say things like, oh, anytime someone executes something, don't let it traverse the path, right? So basically, don't let it write to this directory or any other directory above or below or anything like that, right? You can actually trap those system calls using, again, this is another Tetragon policy that you can set, right? And so again, I encourage everyone to look at eBPF, how it's built into the kernel and how you can best utilize it using tools like Tetragon and Cilium. So when I say Tetragon and Cilium, I say it's amazing that you can use them together, right? So not only can you use like the network policies like how you would normally would in terms of that's always fun. While I'm talking, let's see if we can get this up and running. Okay. Demo gods were not happy with us.
Not enough sacrifices.
Yeah, not enough sacrifices, yeah. Does it actually always go?
Yeah. I'll launch it while you keep talking.
Yeah, so you can use them together, right? So you can use Cilium, as I was saying before, for network policies, but like all the way from like layer 7 all the way down to layer 3 and 3 and 4. But also then beyond that, like when actually workload starts executing, training models, things like that, things that like are happening in the kernel and happening to disk, you can actually also then just like set policies, right? And set policies in terms of mitigating that. We may not be able to get the demo, which is unfortunate. Oh yeah, you have to. If this happens like in the next minute or so, I'll show that to you. But did you want to? Yeah, talk about your segment and then maybe go back afterwards. Yeah.
All right, back to our presentation. So we have our infrastructure in place. We have security in place. Now let's talk about the LLM layer above it. So LLMs will run on the data that you give them. Unfortunately, we have something called AI hallucinations, and they have issues like AI giving you wildly outdated data, like the sun revolves around the earth. The cure to a common cold is leeches, right? There's extremely outdated data. So trying to keep these LLM up to speed and up to date can be a challenge, but that's where U.com comes in. So think of LLM as your smart but static brain. It knows a lot from its training data, but doesn't automatically update itself on what's happening right now. That's where the API comes in. So we have the real-time web access API that fetches the latest web results, news, or other sources in real time. So when your LLM wants to answer a question about something recent, like what's the latest in AI research, it can pull in fresh data. 2, rich context for LLMs. The API doesn't just return plain links. It gives long snippets, summaries, and structured context. The LLM can read this and generate answers that are more accurate, detailed, and relevant. 3, blending multiple sources. U.com's API combines data from different sources, such as web pages, news, etc., into a single response. The LLM can then reason over all the information at once, instead of searching piece by piece. 4, seamless integration. So developers can call the API directly from their LLM workflows. These setups use this in agentic AI, where the model makes decisions or takes actions, because now it has all the up-to-date information to guide those decisions. The TLDR, combine the two, and you get AI that's both smart and up with the speed. Now we have a closer look at what U.com's APIs can actually do and why they're useful for AI and agentic workflows. So Web Search API for the AI's open source models, U.com provides a ready-to-go search interface for open source LLMs, giving them access to live web data without building a search system from scratch. 2, we have the News API. So if you want your AI to know what's happening in the world right now, the API will deliver the latest news and keep answers current for US users and beyond. 3, B2B sources. So companies can pull the most recent product information to improve sourcing accuracy and make better decisions. This shows how search APIs enhance real-world workflows. 4, practical applications. Beyond just search, these APIs support product recommendations, spotting trends early on, dynamic pricing adjustments, and more. Essentially, any workflow that benefits from fresh, structured, or research information can use them. We also recently launched our Research API for more complex questions. For situations where your APIs need more than raw results, the Research API reads, reasons over, and synthesizes multiple sources into a ready-to-use citation-backed answers, making your AI smart and more trustworthy. To summarize, U.com's search and research APIs bridge the gap between AI models and the real world, giving live information, making AI smarter, faster, and more actionable across multiple use cases. So if you look to the screen, I have a QR code to take you to U.com's docs. And we actually provide a lot of free SDKs and developer tools for those of you who want to get into agentic AI or people who want to build chatbots. Like, we have a lot of free open source software that you guys can use. Let's check on this.
Let's see here. All right.
All right, I'm going to let that be on the screen for a little bit.
Okay, cool.
All right.
Let's see here. This is. Oh no, we have to go through this. Hold on. But the. Oh wait, you have the backwards thing. Hold on. I'm old school. I don't scroll that way.
Again, we have the QR on screen, so those of you who want to learn how to make chatbots, those of you who want to get into AI development, plenty of open source tools ready and available, and we also have the developer guide on the docs. So if you're completely new to AI, don't worry, we have you covered.
Okay.
Pun intended.
Yeah. API. What's this here? Test. Okay, that's fine. Wait, do I need to run? Okay, that's fine. Yeah. We're like 15 seconds away from getting this up and running.
Don't worry, we have more time for people to get that QR code.
Okay, and then does that work? Yes, it does. Okay. I can't believe it timed out. That's upsetting to me. Okay. I need to talk to Ralph.
To the manager.
Yeah, talk to Ralph about that. Okay. That should be it.
All right, crossing fingers, praying to the demo gods.
Okay, cool.
All right, the demo is almost ready.
But I can put up this little nice.
Little comic. All right, we're going to take the QR code away in a minute here.
Well, actually, can I? Well, that's starting up. Let's do. Let's go to displays. Ah, okay. Wait, how do you mirror?
Mirror, right there.
All right. And then we're using that. Sweet. Okay, so this demo, and I actually wish I could make it bigger. Can I? Okay, cool. This demo is, we're going to go over how you can mitigate against data poisoning using Tetragon. And this is all running on Kubernetes, using SCaLE and running on Kubernetes. This is also kind of like a sneak peek into Isovalent's securing AI and ML workloads lab, which will have I'll have a QR code at the end, so you guys can get free access and do the lab on your own times here. So here we have a cool little minced digit predictor, right? You write a digit, and then the model kind of tries to predict what number you wrote right here. So some of the answers, actually when we're testing this, I think I don't know if the model was poisoned or if my answers are wrong, so help me with the questions a little here. So how many sides on a dice? I think it's 6. Right? Unless it's 7, unless you're playing D&D, right? So let's predict here. And, oh no, it told me, it thinks I drew a 9. So maybe I didn't draw the 6. Really, maybe it's kind of predict there. I think I drew a 9. Okay, let's get a new brain teaser. Let's see what's going on here. How many chambers in a human? Actually, no, I think there's 4, 3. Does anyone know? There's 4. Okay, I was right in the beginning. All right. Again, I'm like, I think there's 4. Predict, right? And it predicted a 4. Okay, so that's good. What is half of 2? Okay, so 1. This is not very, I think I drew a 1. Okay. And how many sides on a dice? Okay, the question here is predict that. It keeps thinking, I drew a 5? Really? So there's, my drawing isn't that terrible. Like, my handwriting is not that terrible. Let's try to predict that again. I think I drew a 5. So there's obviously something wrong with this model, right? And so So let's, I'm gonna have this little script, right, that'll test the inference model here, and let's see what happens, right? And so I'm seeing a lot of red here. So here, accuracy is 0%, images 9 were predicted as 6s, right? Okay, so we actually saw that when I did it a few times, right? I actually thought I predicted 9. We're seeing a bunch of 5s up there. So we did that here. This is 90%. I think we can let that pass there. Another 90%. That looks good. Another 0%. So it looks like here when you draw 6s, it 5s. So when you draw a 6 or a 9, it looks like it's not predicting that correctly, right? It's getting 0%, right? Anything 90 and above, we think, all right, good, right? It's not going to get it 100% all the time, but now we actually see that there's a problem here, right? And so we're going to do some file integrity monitoring, right? So we're going to let's go to security observability. There we go. So we're going to use Tetragon to kind of look at what happened. And as you see here, if I go up here, if I know how to scroll, a lot of stuff's happening here. File permission, open, file read.
The well has been poisoned.
Yeah, the well has been poisoned here. I can see here there's a read there. There's, let me run that again. Oh, I do tail 50. I need actually tail maybe like 1,000 or something. A lot of stuff going on in Python right now. Okay, here we go. So as you can see here, someone poisoned, right? So, the attacker conveniently called it poison, right? But like this is the demo, so you can see here, someone copied some poison data over, and that's what the inference model is using in order to for the prediction, right? And that's why we're getting those things wrong, right? So, so how do we mitigate that, right? And so let's go into the editor here, and let's do the training model. Actually, let me just copy all of that so you can see here. Wait. Command. So here we're going to do, can I make this a little bigger? All right. We're going to do a policy, right? A tracing policy. This is, again, based on Tetragon. And we're going to say the file, anything in this directory, right? If anyone tries to write anything, delete anything, rename anything, we're going to block that, right? And this happens at the kernel level in the operating system and in Linux. And again, this is based on eBPF. It happens on a kernel level. What ends up happening is that at runtime, right, when it happens, a little program starts up and then basically interfaces against that system call. And so what we're going to do is we're going to apply this policy, and then we're going to try to poison that data again, right? And so let's go to the terminal. Because we love the terminal. Let's do a kube apply there. There's a daemon set, right, that's running on all of that there. And let's try to poison the model here. And if I run that, it gave me an error. Let's run it again. Give me another error, right? It says tar. It says failure due to previous error. It says cannot open file exists, right? So I cannot write into this directory. So why is that, right? So let's go back and let's query this again. And as you can see here, there's this new thing that happened here, that the file delete, right? Both times that I ran it was blocked. Right? So that was blocked. So when someone at the operating system level tries to write data, I have a policy in place, right? Whether they were super user, right? Whether they became root, they somehow compromised the machine, they try to write into it. No, there's a policy there in place that that prevents that, right? So any of you familiar with SC Linux, or at least So if those of you remember, SC Linux is very, very similar to what happens with SC Linux, but this happens at runtime, right? This is not something that is built in, right? This is something policies that you can set, right? So it's not something that you have to write into the kernel. So, and this is an example on how you can use Tetragon to secure kind of like data model poisoning, right? So like the model poisoning examples that I gave, this is kind of one example. We go through all three examples in this lab. So, so when the QR code comes up, you can scan that and do that lab in its entirety when you have a chance here. So let me go back to, we're doing this live. System settings. I don't want to mess up your settings, Angelica, so. Okay, cool.
All right.
I did it.
All right. So I know it was a lot, so we're going to take a minute to review everything. So remember this. Yeah, so basically we went through this whole thing. We talked about data. We talked about the infrastructure. We talked about LLMs, and I talked about APIs. And now we just have the application. And that is up to you guys, because that's something that you guys can create. You can make whatever you'd like. We just set the foundation for you. And here it is all put together. I like to call it the Trinity. So we have Cordant, Kubernetes as the foundation to manage resources. We have in SCaLE with AI workloads. We have the LLMs being fed U.com's APIs. And we have Cilium in the background, keeping data secure and compliant. Would you like to add anything, Christian?
Well, there's a big thing on the right-hand side there called Cilium. And it should say Tetragon as well, but basically, you want to keep all your data compliant and secure. You can do that with existing open source tools. You can do that with tools like Cilium and Tetragon. And now you have that kind of like that foundation in terms of like securing workloads. And that's just generic workloads. We use AI as an example, but you can use Cilium to protect the entirety of that cake, right, as we're calling it.
All right, now, who benefits? So, first, we have platform engineers, which Christian will briefly talk about.
Yeah, so obviously platform engineering, DevOps engineers, system administrators, whatever we're calling ourselves nowadays. This is important because no matter what workload's landing on our environments, right, whether we're running a Kubernetes or VMs or anything like that, we want to be able to secure them, right? Because at the end of the day, yes, it is cool. I am a techie. I love building stuff. But at the end of the day, you have a business to run. Right, you have, we're building a platform for others to use, and we want to be able to have it robust, secure, and available for them. So, for really, platform engineers benefit because it keeps the lights on. We want to keep things secure. We don't want to be paged at 2 o'clock in the morning.
All right, and then how do AI developers benefit from all this? AI developers care about building, training, and deploying models, and they need tools that directly help them run experiments, manage workloads, and get results. So they can use Cordant to focus on models instead of worrying about doing the cluster configs and the YAML files. They can use U.com to get the live web data and research APIs for their LLMs and agentic AI workflows. They can use the API so that at that time they don't waste time scraping, filtering, or curating the data. These APIs are already structured, ready to use results that feed directly into their AI pipelines. In short, the APIs make AI smarter, faster, and more accurate, letting developers focus on building applications instead of managing their data. And then lastly, with Cilium, Cilium shines for AI because AI workloads involve many small, high-performance services communicating under tight security and observability constraints, a pattern that's not common in standard enterprise applications. So I can just build and train my models without worrying about anything with the infrastructure or worrying about security. And then as a thank you, we have the lab available, and on the left, we have U.com free trial. So as a gift to all of you for attending today, I'm giving away $100 worth of credits for free. So scan that QR code, and you can play around with all the different APIs in the API playground. Again, my name is Angelica Ambrosio, and I thank you all for taking the time to be here.
Yeah, and to the right, again, the AI/ML free lab. It's there, provided by Isovalent. Do it at your own time. You actually get a cool little badge. So if you get, if you actually end up doing it, and do a badge. Tag us, right? We're on LinkedIn and Twitter X and I think Blue Sky as well. Do that lab. If you get the badge, tag us. We always love people tagging us there, and you'll get to do the portion that I did, but also everything else, right? You kind of get like the whole story. So it's an inclusive lab. I think we got 2 hours. Make sure you're doing it though, although you get timed out like we did. But you get like 2 hours free in that lab. So thank you as well. So
Thank you so much, everybody.
So we have about 5 minutes left, so we can squeeze in one, maybe two questions. So any questions for Angelica or Christian? All right, awesome. Well, thank you all. They'll be here in case you wanted to ask anything directly. The next talk will be in this room in about 20 minutes at 3:45. And as a reminder, Cloud Native tracks will be happening in Ballroom A and Ballroom B. All right, thanks everybody. And thanks Angelica and Christian.
Check, check. Check, check.
All right. Well, let's get started here. I'm going to talk about a lot of points of view on containers today, and some of them you probably, I don't know, maybe a little less expected, but we'll go through kind of some experiences that I've had and kind of just the way that I've been seeing this ecosystem evolve over time. So my goal here is to rethink a little bit of the last 15 years of cloud native defaults. CNCF, has had birthdays recently. We've been working with containers for a while. There was this whole thing of, are you cloud native or not? And we all had to figure out what that even meant for a while. And so that's what I'm going to talk about. But I'm going to approach this from several different points of view of both long-time experience in distributed systems, long-time experience at different vendors and software companies, and also just experience playing with Unix and Linux and stuff like that, because I eat, sleep, and breathe this stuff. So anyway, I'm Mike Stonke. I'm the VP of Engineering and Growth at Phlox. And my experience started at Caterpillar way back in the day, where I did a lot of infrastructure, ran automation, architecture, things like that. I went to Puppet for 8 years there, did a lot of open source development, did community leads, did engineering leadership, stuff like that. Ran engineering at CircleCI for a little while, like 4 years. And then went to Phlox, which is a Series B startup that is working in the Nix space, trying to change the way that developers do some work. And I've also packaged a whole lot of software. Release engineering is my background, and so I am very much a package nerd. I created this software repository called EPEL. If you've ever used that on Red Hat Enterprise Linux or CentOS or any of that, that was me and 6 other people that decided to get together. We realized we were all doing this at giant companies, and it was not a competitive differentiator, so let's go build something that everybody could use. And so we did. I've also packaged things like I ported Ruby to AIX and all sorts of stuff like that. So anyway, the point is I like packaging software. I've thought about these problems a lot. So containers really ended up solving one major problem. This is what they were really designed to do. And that was developers didn't want to package software. They used to just hand it to somebody else and say, go build me a package. And then with a Docker file, suddenly developers were like, I can give a package as long as it's a Docker file. And now we have a package. And why do we want a package? Well, it's because it's portable, I can distribute it, I can use it different ways. But the issue here is that when you let developers do the packaging, you basically end up packaging the way a developer works. And I'm a developer, and I know how I work sometimes, and I know what stupid mistakes I'm making. I don't wish to embed those in my production systems generally, but here we go. So basically, we end up putting a lot of cruft or handcraftedness into things that end up in production because of the way these containers are built. And not always, because some people have very good process and everything like that. But I will say the possibility is definitely there. The real world scenario is absolutely there of people kind of putting things that were designed for more of a developer environment into something that ends up in production. Now, part of this is not an anti-container talk. I don't think containers are dumb at all. I use them for a lot of things, but I don't use them for everything, and that's kind of the point of this talk. And so by the end of this, I'm hoping that, if nothing else, you just think about this problem from a slightly different angle. You don't need to change your behavior. You can if you want to, but I just want you to think about this problem and be like, there were some interesting tidbits there. Maybe I shouldn't reach for a container the next time I'm solving this problem. Maybe you should. So containers have solved real problems, and I do want to point that out. I really, really like containers. I like the ecosystem. I've worked with it a lot. You got portability, and you got confidence in deployments, because you kind of knew that that OCI spec, or previously like the Docker container spec, which were not the same thing, by the way, those worked really nicely on different operating systems, on different runtimes, on different container runners, and you kind of had a lot of guarantees there, which was great. And so Docker, which came out kind of in 2013, was revolutionary. It definitely changed the way that we did software stuff in every way. And it made shipping software a lot easier, which is great, because shipping software used to be pretty hard. And in a lot of cases, the places that made it really simple had a differentiated edge over the ones that didn't. Or you were handing it off to an operations team to say, figure out my stuff and put it in production to me or whatever. And Docker definitely helped to lower those barriers. And so I do want to give containers their flowers before I start speaking heresy in the church of the container. So we forgot what an OS can do, and this is what I'm going to actually walk through for a little bit here. So Unix, from the 80s to the 2000s, maybe even from the 70s, I probably should have said 70s, but in the 70s, we basically have this multi-user, multi-processor operating system. Multi-process operating system. It's also multi-threaded. If you ever go through like operating systems theory class, they go through all these different like variables on is this an operating system or is this just a runtime? But Unix was awesome. And actually it's still pretty awesome, but it was awesome as well. But you had multiple users on one machine. And so you had this paradigm of I'm going to have hundreds of users on one system. Well, that meant you had to solve a lot of real world problems to do that. And Unix worked really hard on doing that. They had things like, we're going to handle isolation. We're going to have users and groups and permissions and quotas and inter-process communication and user lockdowns and all these types of things. And we ran like that for a long, long time, particularly in academia or in technical workstations areas and things like that. And it worked really well. You could literally talk to everybody else that was logged in if you wanted to over the machine. You could talk to other users in real time, kind of like an instant message, only this was long before there was any type of instant message or text message or anything like that. You could just, hey, you're logged in, I'm logged in, let's chat. And this machine was a shared living system. It usually had a name that was friendly or well remembered. You know, a lot of times these machines were named after like Star Trek or Star Wars or something like that. And so you were like, I'm going to log into Yoda. Everybody else is logged into Yoda. We're going to go talk together on Yoda, or I'm going to go do my work. But while I'm there, you know, late night, somebody else is messaging me because they see a problem and they already know I'm logged in there. And then we got to this thing where VMs came out. And they were like, we're just going to put one app per machine because then we have all this extra isolation. And in a lot of ways, that was super cool because now I didn't have to worry about things like, well, what group is this thing running as? Because no one else was on this machine anyway, so I didn't have to worry if you were in this group or that group or you had rights to this or whatever. And that's really, really nice, kind of. But we threw away the multi-user part. We're just like, okay, VMs are really, they're designed to run usually a single application in most cases. Obviously, there's VDI, and there's definitely caveats to what I'm saying, but I think hopefully you can get the gist of what I'm going at there. So. And then we got to containers, and they were like, okay, we're actually going to do, instead of one user, we're going to go down to one process. And that was also pretty interesting. Had some great value. Had a lot of things that were really odd. And so we had to build up a whole set of different tools to work with that. And so we threw away the multi-user when we got to VMs. We threw away most of the OS when we got to containers. Except we still have to carry an OS around us in the container. So there's like still kind of some stuff going on there. But 90% of this OS is dead weight, where you're not really using it because you're not linking against it, your runtime isn't calling it, your app isn't calling it, but it has to be there just to have a base image in a lot of cases. And yes, I know about from scratch images, and I'll cover that in a moment. But, and so there's just a lot of things here where we're carrying around stuff that isn't part of what you actually need to get the job done that you're trying to accomplish. And when I was thinking about all this, I was thinking about how I think container native technologies are relatively complicated. Distributed systems are relatively complicated. And when I put two complex things together, I get a headache. And so I was working with one of my younger sysadmins at Phlox, and he was logged into a system. And one day I just messaged him over wall. Actually, I messaged everybody on the system. There was like 3 of us logged in. And I was just like, you know, I don't remember what I said. And he slacked me the second I did that and said, hey, I think we may have just had a security breach. And I said, what makes you think that? And he said, well, I was in my terminal, and all of a sudden this text started appearing, and it was like, hi, Brian, how are you doing? And that really freaked him out. And I was like, you've never seen two people talk to each other over a Unix system before, have you? And he was like, no. He's like, how'd you do that? I was like, there's literally this command called talk. So that when I want to talk to you, I type talk. and he was blown away by this because he was just, you know, he was younger. He grew up with containers and all this stuff, and he had never seen a multi-user setup like this before. And as I started thinking about that, we had a long conversation about some of these paradigms that had, I guess I would say, faded away in modern architecture. And I realized that this is a through line for how I've been thinking about this entire set of problems I have adopted so much complexity to solve problems that might not even be complicated. And so he had never seen two people use a computer at the same time, basically was my conclusion there. And so we didn't really solve isolation with containers. We changed the shape of it, though. We forgot this multi-user experience that we had built from the ground up on an operating system that was multi-purpose, multi-user, multi-threaded, pretty darn great. And then we just decided that we're going to use a container for everything. So for developer onboarding, we'll use a container. For a CI pipeline, I'll use a container. For a local developer environment, container. Edge deployment, container. ML workflow, container. When you have a hammer, the problem is the hammer comes with the entire hardware store. And I don't necessarily need the entire hardware store to do the work of the hammer. In fact, I had an operating system that worked really well, that did a lot of these things, before I pulled it all apart and slipped it out into single processes with a full OS that were called these things like containers. So let's go through an example. I have 3 HTML files and a CSS style sheet. I guess CSS is like saying ATM machine. Sorry about that. I didn't look at that. Now I'm mad at myself. So you have 3 HTML files and a style sheet, and this is what you want to package. So I'm going to need a Docker file. I'm going to need Nginx in this Docker file. I'm going to need a registry to store the image. I need an orchestrator so that I can run the container. I need a service mesh so that I can talk to all the things. I need an ingress controller so that the things can talk to the other things. I need a secrets manager because I have to go get stuff in a config map or something like that at some point. And a CI/CD pipeline to build my own container. And then I got to scan the container to make sure that it's production ready. I got to have a policy engine to make sure I'm allowed to run this container on these right nodes. I need observability tooling to make sure that none of that stuff failed in that entire process. And a team to maintain this platform that this all runs on. And I had 3 HTML files and a style sheet. When I used to use Unix, I dropped this in a folder. It was called public HTML. I was done. We did not make this better. Okay, let's do another example. I have a function that runs once a day. I ship it as a container. It's a 500 megabyte container. It goes up to Lambda. Lambda runs it. Or I could have had a 5 megabyte zip file and not included the entire OS with it, and it probably would have done the job. Now, Amazon wants me to build that whole container, because every time I ship that 500 megabytes back and forth, they charge me more. I don't know if you've ever looked at cloud bills of any significant size. Network is the sneaky one that always gets you, because you can plan for compute, you can plan for your RDS, you can plan for your storage growth, and then networking, it's kind of a hodgepodge, because some months you're doing a lot, some months you're not. You're moving stuff around, you're doing migrations, whatever. But the point is, networking, it like looks super cheap until it's not. And so these incentives are not aligned. Basically, the ecosystem players, the major hyperscalers, are actually incentivized for you to use containers because of their inefficiency. I'm incentivized to be more efficient because I like that. I mean, I'm not paying the bill. Some company's paying the bill, so I'm not that concerned about that part of it. I mean, like, I'm concerned if I'm measured on it in some way, or it's my responsibility, but generally, it doesn't come out of my pocket. But this platform profits from our inefficiency. And that is why 3 of the richest companies in the world are cloud providers. And they continue to profit off of our inefficiency. Doesn't mean they're bad. Like, it's their business model. It's fine. I just don't necessarily want to do that all the time. And then beyond that, you have this complexity tax, which I started to unfold as I was walking through my HTML and style sheet examples. So this is a partial view of the CNCF landscape. At this point, it is not possible to fit this on a monitor because you have to scroll both right and left and up and down because there is just so much stuff in the CNCF. When I look at this, I do not see good things, I will say that. It's not because any of these vendors are terrible or anything like that. They're not. I'm just like, wow, I have to look at that much stuff to understand stuff. That's a lot. So no single human can understand all of that. You may be super deep in the observability space and know who most of the players are there and most of the tools and most of the projects and all of that, but you're probably not then super deep in that CI/CD space or something else over there. It's just too much. And so with every problem in this cloud native stack, we've created a new abstraction. We have a complexity tax, because every time you add an abstraction, you both have a new mental model of how to think about it, but also new debugging steps you have to take to break the abstraction to understand when it's not working. And so we didn't ask to stop, is this layer necessary? Or maybe it was necessary from 2013 to 2017, but in 2018 we had solved it with a new version of something and we didn't need that layer anymore or that tool anymore. And I don't see a lot of those tools coming out of the stack. I see mostly tools being added to the stack. And so we rebuilt the OS, but kind of worse. With process isolation, we have containers and orchestration. With process supervisors like systemd, we have Kates controllers and health checks. With inter-process communication, we have service message and gRPC. With logging, you have things like Elk or Fluent or Loki, and there's like a million others. For things that were like PS and Top and strace, we have Prometheus and Grafana and OpenTelemetry. Like, so you have all these tools that kind of map to these primitives that came right out of Unix. And for user permissions, I got RBAC and OPA and mission controllers. And for file system permissions, I have Vault and sealed secrets. And you say that one doesn't make as much sense. And when you think about it, the reason you have secrets is so you could load them into an environment, whereas if you had an environment that no one else could see and it was isolated, you wouldn't need to load them in that way, because basically they're all in runtime in memory anyway. So that's why I put that one here. It was a little weird. I had to think about it for a bit. Cron, you have Kubernetes cron. Like, they even labeled it the same thing. And then you have like talk and wall and signals that end up being more or less webhooks and event buses. And DNS. Okay, so basically you end up with, I have rebuilt all of Unix on a distributed cloud-native platform where I've externalized everything that was built into the operating system so that I can ship an entire operating system inside of a format to run a single process. Why? I don't know. All right, so we didn't add capabilities, really. We decomposed a working system, and it worked quite well. We reassembled it from 1,000 vendor-sponsored pieces. Like, it's like we had all this stuff that was built in the OS, and now I can buy each one of these things separately. I can maybe use open source stuff with it separately too, but there's a lot there. All of those things I can reassemble to give me basically what Unix used to do since the 70s. Cool. And then containers got used for other stuff. And I like to say it's technical debt laundering, but I usually get into default swap derivatives. If you're actually into how the economy collapsed in 2008, that was basically what it was. It was trading on default swaps. And default swap derivatives were basically this idea that this person wasn't going to pay their mortgage, and I'm going to bet on it, and you're going to bet on my bet on that, and we're going to trade it around back and forth until we're all happy and make money, except no one makes any money, except then the government bails you out, so everybody makes money. I think that's how that worked, right? We all got better off of that? Yeah, okay. So if you have a messy application, you can just throw it in a container. There are entire companies that make their money doing this. And honestly, I almost started one at one point where I was like, ooh, you know, the first person to put SAP in a container, they're going to make some money. Person to put JD Edwards or PeopleSoft, things like that in a container, they're going to make some money. And I really debated about going to do that. I decided I liked myself too much and didn't do that, but I think the money would have been pretty great. But the debt doesn't go away from taking these legacy applications and putting them in a container. What you did is you put it in a little box with a label. And you're like, hey, this is my debt. It's in the shoebox. It runs over here. Cool. And so this is the equivalent of basically shoving everything in the closet before the guests arrive, because your house looks really clean, because you have these nice containers. But then you open the closet and everything falls out. Because you still have all the problems that you had before this thing ran in a container. You just have a new shape for the deployment. And so, if it works in the container, I stop investigating why it was broken, whatever. I didn't fix my dependency messes because I just took everything in there and swapped it and threw it in the container. So we baked in all of our problems into a file format, and we called that an image. That's fine. We're going to come back to that, though. I'm going to talk about a story that was real life. So like I said, I used to run engineering at SCaLE. How many of you use SCaLE? Anybody? Okay. I think it's a really great product. But I ran engineering there, and we were having an outage. And it was complex, and I was frustrated, and we couldn't figure out what was going on. We had 6, 7 services that were down. We couldn't figure out what was going on. And the place we saw it first, of course, is where you start your debugging. Well, I first started to see problems over here. Okay, so you do that. And an error shows up in service A. But the problem was 7 or 8 handoffs before that service. There was a cache that where the disk was full on, and we were not monitoring it properly. Also, isn't it funny that with the most complex distributed systems in the world, the problem is still my disk fills up? Yes. So we have not solved that problem in all ways. And so this expired cache was in a service that nobody was watching because it was one of our first deployed services as we were like ripping apart a monolith, as one does. And that one didn't get all the same monitoring and observability patterns that a lot of the other newer ones had because it was one of the first ones we had done, and apparently we hadn't retrofitted all of that stylistic pattern on top of that older service. Again, I think that's relatively understandable. It happens. I'm not like, trying to lay blame here, but the issue is that that took us more than 2 hours to figure out that this service over here looks really broken. And the reason it's really broken is because this cache isn't returning a hot hit like 95% of the time, like it usually is. And so debugging took a lot of heroics. And that was the first time that I think I really, really, really got frustrated with the cloud native architecture on everything. I was running like 30,000 nodes in Kubernetes. So like, I was doing this in a big way at scale, and I was just like, this is not working for me. This is not working for a team of experts, and we were really good at software engineering. We're deploying like 500 times a day at times. Like that's how fast and how good the testing was and the validation, all of this. But this service was broken. It was going through 5 other handoffs of like gRPC communications and all that kind of stuff. And then over here, there was a cache miss that was happening at a way higher rate than normal. And so it was impacting performance, and that performance was compounding, and it was impacting hit rates on other stuff. Other stuff was timing out, and that's why the users couldn't do their work. Sucks. So, file's missing because I wasn't getting a cache hit. On a simple service, I would have been like, hey, let's look at this PID. I run strace. Hey, it keeps looking for this file. It's not here. Oh, huh. Wonder why that is. I'll go look at the source code. I'll put it in there. We'll be done. Maybe it's a config file, whatever it is. So the complexity doesn't just make building harder. It makes operating more difficult as well. It makes debugging dramatically harder. By the way, operating and debugging are the same thing. So whenever you hear somebody talk about operations, you can just think about the debuggability of the system that is online. And if you debug, and you do debug more than you build, I guess is the point. Particularly now with AI accelerating how fast software gets developed, you're actually spending less time on that raw development than you probably ever have. And I already thought that was the easiest part of the entire SDLC. Now we have operating software in perpetuity. Operating software, keeping it online, keeping it secure, keeping it up is difficult. So we got the distributed monolith. That was basically the story of that set of services in Circle CI. Was we had thought we had ripped it apart into microservices, but we hadn't. Because if something failed in one service that was 8 services over from another one, 2 services had failed. And it turns out keeping 2 things online is more difficult than keeping 1 thing online. You can double check my math on that one. And so I got all the complexity of this distributed system, and I got all the coupling of a monolith. And that means I couldn't deploy things independently. We actually did deploy them all independently, and then I was pretty proud of that for a long time until we had an outage that looked like this. So from there, we have synchronous call chains. They're 8 services deep. We have a well-structured monolith. I would have been 1 strace away from the answer. And we did have a well-structured monolith that we hadn't pulled everything apart. And honestly, debugging that was much, much simpler. But we put this monolith into microservices, and we got a distributed monolith. And I would say that's worse because now I have 2 problems. And I usually summarize this with, it might not be good, but at least it's expensive. And then we get to the sidecar explosion, which is I wanted to deploy 1 thing, and I am running 4 things. And 4 is just an arbitrary number, not exact. But I have like an application container, I have a logging sidecar, I have a service mesh proxy, I have a security sidecar, and all I wanted to do was run my app. So I can write a log file, but I have to launch that sidecar to be able to write the log file. There's just a lot of difficulty and complexity here. And then there's the monitoring paradox, which is the more complex a system, the more monitoring you need. The more monitoring you have, the more complex the system is. Because monitoring tools also require monitoring. And so some orgs spend more on compute, like more compute power on observability than they actually do on their real workloads for customers. And I can say that the ones that do, like it's fine, that might be the right choice, but I know that some of my observability bills when I was running engineering at my last company were very, very, very large. And I say that comparatively even to some of the cloud bills and things like that. So, and then we have these other things that could do observability or monitoring or system debugging or whatever you want to call it, where this stuff was all there. So you need monitoring for your monitoring, and we've optimized all this for developers. I would say that containers was an optimization for developers so that they could package things quickly, and they could basically say, I have figured out how to do things, I'm going to put it in a container, and that container will be the thing that we'll base our foundations on to run our application on. A totally noble cause. I'm just going to say we may have missed a few spots. We forgot about debugging, and we added it on later through all these layers of extra tooling. We made it trivially easy to ship something that nobody can troubleshoot. And I find that a little bit difficult. There's also container golf. This is one of my favorite side sports. How do you get your container to be as small as possible? Well, you can do Alpine, you can do distro list, you can run it from scratch, you can do all sorts of cool things. But most people have a base image they use somewhere. And they just say, we have a base Ubuntu image, or we have a chain guard image, or whatever it is, we have something that we use, and we just have a base image. And we don't do from scratch because it would be very different depending on what the application was, or we don't do distro lists because of the same problems. And so this practice of container golf only exists because of containers. Obviously, we wouldn't have it without it. And with this, you actually scan your image and not your container, because your containers go out into production. And I don't know if you know this, but you can actually change a running container. And from there, that scan that you did on that image is unimportant, I guess would be the way I would word it. And people say, well, you shouldn't do that. You shouldn't edit your containers live. You might not, but your application might be. And so that's the thing to think about as well. Latest. By the way, mutable tags are my least favorite part of the entire Docker ecosystem, and it's not particularly close. Anytime I can have latest mean something different today than it did yesterday, latest has no meaning. I do not know what that means. I do not know how to figure out where it is. I hate it. I hate it. I hate it. Tags should not be mutable. They should be immutable. It's a release engineering theory thing, and it is right. I will not be taking questions on that at this time. So, so apt gives you different updates on different days. And so like a lot of times in a Docker file, you might say apt get install, dependency 1, 2, 3, and 4. You do that Docker build last week, you get a set of software. You do that Docker build this week, you get a set of software. Those are not the same set of software, or there's no guarantee that that's the same set of software. You can pin every package you want in a Docker file. However, that is extremely difficult to do on most distributions. A lot of times you can pin the leaf node, but you can't pin everything that's in the tree trunk because it might be, well, libc updated underneath, but you didn't pin libc. You actually just pinned your version of Python. Things like that. And so a packaging format with some reproducibility, a packaging format, the same reproducibility, read the slide, I'm not going to be able to. All right. And we're about to do all this again with AI. That's the thing that I'm getting scared about, is like we have these GPU model serving containers that are 15 gigabytes. So instead of like maybe a 1 gigabyte container, we're like, let's do this like 15x more. And we just ship it all around everywhere. We're going to spend way more on networking. We're going to spend way more on storage. And the hyperscalers are going to get way more of our profit because we chose the wrong tool for the job. So we have the same golf where I'm getting only I'm doing it at 10x to 30x the size on the container. Now I'm going to get into one other problem, is that we have frozen entropy inside of containers. There will be like a wrap-up where I solve a lot of these, or no, maybe not solve. Solve's a strong word. I get you to think about it differently. But let's just say I have an application. It needs Python 3.11, Node 18. Everything works, and we ship it. OK, cool. Months pass, years pass. It still works. It's running. Everything's great. And this is one of Isaac Newton's lesser-known laws, which is a system at rest will remain online. And this was classic. Like when I come from a Unix heritage, this is what used to happen. It was you got this thing to work. We're going to put it on HPUX. It's going to sit in the corner, and no one's going to touch it for 4 years because it worked. And if you touch it, change is what causes problems. Lack of change can also cause problems, but there's a different type of problem that can solve or have. So you might be getting new vulnerabilities that are discovered. When people say you're accumulating CVEs, I'm like, no, you always had all those CVEs, they just weren't known. They were always there. So containers kind of just let you freeze this entropy, which you're like, that's awesome, I've got a thing that works, so it's not gonna change, it's stable. Except you've also frozen your security posture. And so you have this image, you may have been using it for a while, maybe it's 6 months old, and you still keep deploying it because it's got the application configured perfectly, and all I have to do is load in the right config map, and it runs, and it does everything the way it's supposed to do. All right, that's fine. Containers didn't make us lazier about this. We did the same thing in the Unix world. We just let the system sit there in the corner, and we're like, don't touch it. Fred's on vacation for the next 4 weeks, so we're not gonna make any changes to this system, okay? So they just made it basically easy to stop moving forward, and we conflate, I'm not going to do anything, with stability. And those are, again, not necessarily the same thing. They're not unrelated. But what we lost in here was a forcing function. And I don't know if any of you have ever worked with like hardware data centers or your own stuff where you've touched the server and done the work. There used to be this thing where hardware had a life cycle. Might have been 3 years, might have been 4, might have been 5, whatever it was. At some point, you were like, that hardware has to leave the data center, and we're going to get new hardware in the data center. And when you did that, usually that forced the operational capacity teams to be like, well, this is when we put on a new OS, or we have the latest patches, or we update to the latest version of this application, or whatever it was. And so there was all of these moving parts that meant those hardware migrations were a forcing function that often took 9 months or a year to plan and execute and all this kind of stuff so that you could upgrade your application. I don't miss any of that, by the way. But the nice result was I had a maximum window where I could hold something kind of the same way. Whereas right now, if you want to run a container of Ubuntu that came out in 2013, because it just worked and did everything you wanted to, it probably still runs. And again, in some viewpoints, that's a feature. And in some viewpoints, that's a liability. I can't tell you which it is for you, because it might depend on what you're doing with it. And then there's finally this problem that I have with YAML. We configure the most complex distributed systems on Earth with a white space significant language. Oh my God. Why? Why? No, really, why? I have no idea. It's a really weird choice. Anybody know what the Norway problem is in YAML? It's that if you have a list of countries and you use their abbreviations, Norway is NO. What does NO evaluate to in any YAML library, say pre-2019? Well, it's default, it evaluates to false. So no is false. So Norway is false. So I can't have a list of countries. And even if you quote it, it'll still evaluate as false in some cases. It depends on which YAML library parsing you're using. Oh, and this was fixed in the YAML spec in 2013. The YAML libraries that are most commonly used today still do not honor that. So like the one in Python, for example. Today does not use the YAML spec for 1.2, uses 1.1. This problem exists. I hate it so much. And then inside of this YAML, because YAML is not a programming language of any kind, it's a serialization language, we invent dialects of programming to put inside of it, which makes me sad. It also makes it so I can't read it. It also means that I don't know how to validate it in any way unless I'm using a very specific tool to validate a very specific type of YAML with a very specific templated programming language inside of it. And if I'm going to have specialized tools for everything, I could have done this without YAML. I could have used just, hey, this is the configuration for the way that we set up controller Y or whatever. So it's like programming, but it's worse because I've got no type system and no compiler and no debugger and no validator. And people are like, but you can put it in your editor and it'll show you if things are lined up right. And I'm like, cool, I have no schema to know if it needs to be in this indent. Is it an array? Is it a list? What is it? I don't know. And this is why I don't like YAML. And then there's the final thing. It's like, well, the reason I chose to run this giant CNCF stack is that I need to be able to scale. I will challenge you and say you probably don't have a scale problem. I know the company I currently work for, we could serve out every piece of traffic that we get all week on a Raspberry Pi with a cell phone modem, and we'd be fine. And it's not because we don't get that much traffic. It's because a Raspberry Pi with a cell phone modem can handle an awful lot if you know what you're doing. And instead, people are like, we're going to need thousands of nodes doing Kubernetes or whatever, or maybe just a couple, but it's a lot. So Kubernetes was designed for something like Google SCaLE. That's great. They have really weird problems. They have really hard problems. If you've ever worked somewhere where you have to dig into TCP and change the way it works, you do have a SCaLE problem. Congratulations. But you're probably not Google or Meta or a lot of these companies that are scaling in that to that degree. So you may have an adoption problem, though. You may have a revenue problem. You may have a product market fit problem. You may have a unit economics problem. Like, all of those seem more likely to me than a SCaLE problem. Scaling is late stage. And you might say, I work at a super mature company. We are doing things at scale. That may be true. Your next business line might not be mature. It might not have the scaling problem yet. It might be, okay, well, this business line, this new thing I'm going to deploy, does it need to go to Kubernetes day zero? Does it not? I don't have the right answer for that. I don't know your politics. I don't know your inside architecture, requirements and all that. But a lot of times you can move a whole lot faster with an HTML file and a style sheet in a directory than you can with a container and a pipeline and a scanner and all of that stuff. So if you have a SCaLE problem, congratulations. It actually means you're successful, probably. Or you're really bad at handling traffic and tuning. One of those. But premature scaling is premature optimization. And if you go back to your CS theory classes, Donald Knuth will pop up, and he will say that premature optimization is the root of all evil. There's more to that quote, but that's the pull quote part of the quote. So, and then Kubernetes also had this multi-cloud portability myth to me. We'll use K8s so that we can run everywhere. My favorite part of Kubernetes by far is that it's a standard API that so many applications have adopted and used. That is awesome. Working the same way, great. Got no complaints about that at all. The issue is that almost nobody does cross-platform cloud portability. Who runs on a Kubernetes provided thing across more than one cloud provider for production workloads? One person in this entire room. Your Terraform is cloud specific. Your monitoring is cloud specific. Your billing and billing analysis is absolutely cloud specific. And so you're not jumping back and forth, even though you were like, this is this common abstraction. You're right, it is, until it's not. And so we traded vendor lock-in for this ecosystem lock-in, where I have to use Terraform in this way with these providers, or I have to use these logging things or these billing analysis tools or whatever, and some of them are cross-platform and some of them do an okay job. But generally, most people don't actually do production workloads using the same tech on different clouds. So we've added this K8s layer with the theory and promise of portability that no one's using, one person's using. And now we need a platform team to manage this portability layer, even though we've never actually done anything to be portable. This is, again, adopting complexity to solve a problem that I don't have. And then you get into resume-driven development. And that's, I need to have Kubernetes experience so that I can get my next job. Oh, that's real. That's super real. And it's not evil. Like, if you need to know Kubernetes because you're like, this is how I put food on the table, hell yeah, go learn Kubernetes. It's awesome. You should do that. It's real, and it should be named. Like, we should say, there are people that are doing things for companies because they think it's how they're going to learn and advance their career the best, whether that's advancing their career at the company they're at or jumping to the next one or whatever. I work mostly with startups these days, and startups that start on Kubernetes, I get angry at. I'm like, why would you do that? You don't even know what your application is that you're building. You don't even know who your users are yet, and you're spending a platform team? Like, you're building 2 or 3 people? You're paying like $600,000, $700,000 a year just for the humans to go build this thing? That is misallocation of funds at worst, or at best. And so the other thing is, once Kubernetes is in, no one wants to remove it because they feel like they're being heretical. And so if your career rewards complexity, who's incentivized to simplify this stuff? Sadly, it might fall to management, and we all know how that's going to go. I say this as an executive. So you kind of get this cloud native gatekeeping thing where it's like, hey, if I don't use containers in Kubernetes, I'm not cloud native. And if I'm not cloud native, I'm not modern. And if I'm not modern, I can't attract any talent. And if I can't, oh, wait, you're still running VMs. That's legacy. Oh, I don't want to work there. I thought everybody cool was doing containers. I thought everybody was doing Kubernetes. Sidebar. Do you ever realize how legacy is a great thing in every other industry other than technology? Yeah, legacy applications are awesome because it means they're currently making money. Because if they weren't, they would be turned off because you hate them. So you're using a monolith. Well, you'll never scale. This is a counter thing I get. I can tell you that some of the largest systems in the world that you use on a daily basis were monoliths for a very, very, very long time. Some probably still are. Reddit for a long time was a monolith. So Twitter for a long time was a monolith. And it doesn't mean that at some point you shouldn't pull it apart. But those things had scale problems. That was why they pulled it apart. They found users, they found product market fit, they found initial revenue, all of that kind of stuff. But there's also like questioning the stack is like, well, if I question, should I be running on Kubernetes? People start to question me and my credibility. They're like, well, do you even know what you're talking about? Everybody's doing this. That's weird. And so I just start saying, let's judge by the outcome, not by the labels, not by the tools. And then finally, the common rebuttal that I get is, well, if you think Kubernetes is so complicated, get good. Skill issue. Okay. I mean, there's some validity to that. I don't play with Kubernetes every day. I find it annoying, and I kind of hate it in a lot of cases. Not because it's a bad tool, but because I have to go through a lot of steps to do the things that I'm trying to do on a very regular basis. Now, in production, do I use Kubernetes at times? Absolutely. It's fine. Do I use it for everything? Absolutely not. So, I hear, Kubernetes isn't that hard, get good. Okay. Or I hear, if you've done Kubernetes for 10 years, it's like second nature, you don't have to think about it. Okay, I believe you. But I also think you should understand the systems that Kubernetes runs on, and that's the layer that you could actually operate on, and it would be simpler. And your expertise is, if you have expertise in Kubernetes because you've been doing it for 10 years, it's not necessarily transferable to the next set of people that's working. And so you may have a 10-year advantage or a head start, but the next person has to absorb all of the things you've learned to be successful with what you're doing. That's rough. And so it's easy for me ends up basically being a survivorship bias. You've done it, you've worked on it, you were successful, therefore it's easy. Cool. And so the question isn't really, can an expert operate this? It's like, should it actually require an expert? This was a long conversation I had when I was running a large engineering team. And it was the job of a staff engineer is to make this system easier to work on by everybody else. That's the job of a staff engineer. And if the staff engineers aren't doing that, it's all just sparkling software development. So instead of being technology oriented and anchoring my career around saying I love Kubernetes or I don't, or I love Nix or I don't, or whatever, I look at outcomes. Are you solving the business problem? Are you getting the revenue you're supposed to get? Or are you getting the information out? Are you learning the things you want to learn? Not everything's about revenue. It could be, hey, I actually just wanted to learn about how this technology works. Then you should use the technology if you want to know how it works. Like that, there's no other way to do it. Or it could be, I want to have a home lab and I want to play with all these complicated things so I can figure out how they all fit together. Totally valid. But the best infrastructure basically disappears and is out of your way. You don't think about it. You're like, I can go do the workload that I want to go do. So what could be different? Network costs. Containers at the edge, full images over constrained networks. Anybody do IoT stuff? Anybody run Docker on like really small nodes way out on the edge? There are a lot of people that do. A lot of point of sale stuff does, stuff like that. If you have a Docker file, and let's say it's like 50 lines long, and you change line 25, every layer after line 25 is now new, which means I'm shipping at least 25 new layers out to that IoT device that probably isn't on the best network connection. There are other ways to solve this problem. For example, if I use Nix, when I work at Flock, so I like Nix a lot, big surprise. I could change the one package that needs to change, and I can ship you that instead of changing this entire image. And so let's say that image is 500 megabytes. Well, let's say the package you change is 3 megabytes. I can send 3 megabytes instead of changing 500 and shipping 500. That's cheaper on network costs, it's cheaper on bandwidth, it's faster. So there's just all sorts of good things there. Yeah, I guess that was the example I just walked through. When bandwidth is expensive, this isn't just academic, it is a budget. And you start to look at this, particularly when you're sending stuff into weird regions that have very weird network costs, ins and outs, ingress and egress. How many people run Docker on like super small machines? Anything like less than a gigabyte. Anybody running Docker around things with less than a gig of RAM? I do it all the time, but I'm just curious. So, okay, a few of us. So know your options. There are some other options here to solve other problems. Bare metal VMs with good config management. Still a pretty good idea. Systemd units. Yeah. Systemd is not without its flaws, but generally pretty awesome. Single binary stuff is really cool. You can use Go and Rust, and I like that they say they have no runtime dependencies. Go and Rust both do have runtime dependencies. You just don't always know what they are. Usually it's Etsy services, which is part of the IANA standard, because if it's ever doing a lookup in networks, it needs it. Etsy time zone is another one it usually needs. Doesn't always tell you that. Just know that if you're ever doing things from scratch. So you can run Nix closures or Flux environments. These things are like containers, but they're smaller, or they're different shaped, and they have different properties. I'm not here to sell that to you, but they are an alternative. You can basically have your complete dependency graph computed and have it all the way down, be completely hermetic. And that means I'm not shipping this OS. I'm only shipping the exact things that my call path goes through in my application. And so basically ship what you need instead of the whole OS. There's another thing of Firecracker and micro VMs. Anybody played with this stuff? Firecracker, micro VMs? This stuff is super cool. You know, when you can pause VMs for milliseconds in between transactions and stuff, it's actually really, really cool. AWS built this because containers weren't the right primitive to build AWS. They were like, the isolation isn't sufficient. The inter-process communication doesn't work for us the way we want it to. We actually want to be able to pause things and pause the network layer at the same time as the process layer. Like, there's all sorts of things that they did. These things that are boot up in like 125 milliseconds. Anyway, this tech is really cool. I'm excited by it. I want to play with it more. Yeah, so when the cloud providers needed isolation, they didn't reach for containers. WebAssembly. Anybody doing a bunch with WASM? Anything with WASM? Okay. I've done a little bit. This is something I want to spend more time on as well. I think you have some neat deployment paradigms here. Solomon, the guy who created Docker, basically said that if WASM had existed, he wouldn't have needed to create Docker. What? Just think about that for a little bit. If WASM had existed earlier, we probably wouldn't have Kubernetes today. That tells me that might be something I want to learn more about. You know, these are modules, they start in kilobytes, or they're usually in kilobytes. They are small, they move quickly, they start in microseconds instead of, microseconds instead of in nanos? No, milliseconds, sorry. I'm gonna get that right. Metric, I'm American, it doesn't work out super well. Portable. So these are sandboxed by default with WASM as well. And it's still early on some of this stuff. Like some of it, for certain categories of workloads, WASM works super well. For others, there's definitely still some growth there. And then, of course, you still have containers in Kubernetes. And when you generally need it, it's great, especially if you already have a huge understanding of it. If you're great at debugging it, it's great. And the menu of things that do work is longer than people realize. Not everything needs to be a container. Not everything has to run in Kubernetes to make you successful. Multi-user Linux or Unix is still a thing. The OS still knows how to do this. It didn't forget. So let's look at a little bit of a decision framework. What problem am I actually solving? Let's start there. Does the container solve it, or does it just defer the problem? What's the complexity tax, and who is going to pay that tax? Could a simpler tool solve it with fewer layers? And am I choosing this because it's right, or because it's the default? If you ask yourself these questions when you're developing your next set of technology, you may just find yourself at an answer that isn't, I will use a container and Kubernetes. It doesn't mean that that's the right answer. I'm just trying to make you think about different options. And then with AI, we're going to make all of these mistakes, but now at new speeds. So, how do I serve a model? I put it into a container. Cool. So if I change one layer on that container, I have to ship that whole model around again. Oh, that's awesome. Yeah, these images, 15 gigabytes. When we were at KubeCon, I was doing a poll of what's the largest image anybody had ever shipped. 488 gigabytes was the biggest one that I had heard at KubeCon on the floor. So if you've done one bigger than that, I do want to hear about it, because that's great storytelling. But it's just like, if you're shipping hundreds and hundreds of gigabytes, what are we even doing here? Like, that is probably not the way you want to do some of that. With AI, we're getting basically complexity, acceleration, accretion, 10x the speed. And AI could break the cycle, because there's also some help here. What if AI can solve some of the packaging problems? remember, we went all the way back. Docker, really, the value of Docker was this, I could package software more easily. And packaging meant it was portable, and I could query it. I could figure out what was there, why it was there, things like that. Okay. So instead of put your laptop in production, I could say, hey, here's my workload. What do I need to run this in a production environment? Maybe you get interviewed. Maybe it asks you a set of 15 questions, or the 5 that I gave earlier, and then you can say, oh, okay, that's the one I want to pick out the other end. You could make a wizard for that. So what we learned from these 15 years of basically picking a container as the default layer for everything that we're doing, when we come through the AI experience? I'm not sure. Or are we just going to sleepwalk into the same patterns now that we're doing everything with different tools? In closing, you have permission to question the defaults. You can question them from your peer group, from the industry at large, from your friends, but you are up against the most powerful force in the universe, which is called organizational inertia. If you've ever tried to change anything at a company, you know what I'm talking about. It is hard. And I say this as a guy who sits in a VP chair. It's hard there too. So this is how we do it is not an argument that I want to get into with engineering. And it's not about blame. I don't think anybody was ill-intended when they said we're going to use Kubernetes or we're going to use containers or we're going to add a debug pod to launch under these conditions and whatever. But if we knew what we know now, 15 years ago, would we be making the same set of choices? It's a simplification. That's what I'm asking for, not a regression. This ecosystem is incredible. There's a whole foundation here. There are conferences, there's learning, there's education, there's neat tech. I do not want any of that to change. I just want you to think about, is that ecosystem the right one for every workload that I'm ever going to deploy and we're in use? So the market maturity isn't adopting every tool. It's knowing when you should put one down. The goal really wasn't ever containers. It was shipping reliable software for the people who need to use it. If a container gets you there, do it. If something simpler gets you there, do that. So stop asking, how do I containerize that? And start asking, what does this actually need to run? Please be outcome-oriented and resist the pull of the defaults. I am Mike Stonke. I run engineering at Flox. And I think I am done for now. So thank you so much. Yeah, we can take a question or two, I think.
Let's see. This is going to be a bit of a back and forth.
I really love your talk. I think that a lot of us really resonate what you said about a lot of it. But I want to ask you a question. So let's say you are an engineer, right? You want to build, you're tasked to build things, and you want to do what's best for guests, but you have a set of tools that you're told to use. In particular, my company is looking to move to Kubernetes workloads, which, I get what they're trying to do, but I think their timeline and giving every engineer a hammer doesn't really solve the things that they solve, and you address a lot of reasons why. So my question is, let's say I get an elevator talk pitch, with the someone who is green lighting this decision, but he doesn't necessarily know the impact of this. What is a good way for an engineer who really wants the best for the company and guests to explain to him, to have him think about the impact of this decision to put everything in a container just because? I hope my question makes sense.
Yeah, no, it makes total sense. I think, just to summarize and play it back, it's basically, if all the engineers are doing it this way, and that's the set of tools that I'm handed, isn't that kind of the option set that I have? And it might be. But it also could be, okay, we have one way of doing things. We could add a second way, which is a complexity, so that might not always be the right answer, but it could be we have kind of the lightweight, simple way of doing things and the more complicated way. For example, like where I work currently, we ran a lot of stuff on fly.io for a while because it was a simpler interface to do a lot of stuff before it ran on a more complicated, cloud native type environment. And we did that until we either ran into a problem with fly.io just didn't have the options of things that we wanted to do anymore, or, and part of it was also just the network transfer costs of going in and out of AWS and stuff, and so we were just like, okay, for optimizations of a different kind, we ended up changing. But if you can run on something like Fly or Heroku or something like that, that's a simpler way of doing things. And so you might look at that as an alternative, but it also could be, okay, we just have a big Unix server that we can all use as development, and that allows us to iterate really fast. And maybe in production, you still deploy to Kubernetes. That might still be an okay answer. Like, I don't have necessarily a perfect answer there, but even if you just think about the problem, even if the outcome is still, I'm going to use Kubernetes, you've at least thought about it a couple different ways. And you might just think about, okay, I'm going to use Kubernetes in a simpler pattern, maybe for certain workloads, than having a full service mesh. Like every time I hear the word service mesh, I basically think, oh my gosh, debugging is going to be terrible. And so maybe you can do it without a service mesh. Like, there are things like that. So, do you want to take the? Yeah.
Can I be terrible and do a comment and here? One of the apps that I work on, we have a server. It has MySQL and PHP installed through system packages, and we deploy through rsync. It just works. It's great.
I have many like that, except for the PHP part. But so.
All right, that's going to be the one comment exception. No, I'm on to you. Any other questions?
All right, well, thank you very much.
All
If
right.
you want to talk more, I'll be out in the hallway or whatever. So thank you.
Thank you.
Testing. No, no, I'm going to.
Hello, everybody. Oh,
You preempted me. That's good. That sets the tone really well. Screen, I think, just went off.
I'll fix that.
All right. So this is the last talk. So Dave stands between you and your dinner. Director of Developer Relationships at Ampere Consulting. He runs the developer relations as well as helps promote ARM64 servers for all cloud application needs. Welcome, Dave.
Thank you. Ampere Computing, so not consulting, but we're a CPU company. I'll tell you a little bit about Ampere in a second. You're not that interested in me. You're interested in continuous delivery and multi-architecture applications on Kubernetes and how we can make that easier. So I'm going to go through a lot of stuff here. But in general, I'm going to start with a brief introduction to Ampere. I'm going to talk about how the cloud has changed software delivery and the reason why we have continuous delivery in GitOps. People probably already know that, but I'm going to gauge the audience as we go along. And I'm going to bring it all together and run through, if you've got an application that works on x86, what you need to do to get that application running in Kubernetes on an ARM64 pod. So very brief introduction to Ampere. For those of you who are unfamiliar, Ampere makes CPUs. We design from the ground up CPUs with lots of cores. So that's kind of the three core tenets of Ampere. We build products for cloud service providers and for hosting companies, for enterprise, with high core count, low power draw. Low power draw means easier to cool, and it means you can have more cores per rack. It means you have more cores per unit of volume. So, the company's been around for 7 years. We were recently acquired by SoftBank, and this was the vision of the company. We've been working on this x86 architecture for 40 years. It's a company that's it's an architecture that's picked up a lot of functionality along the way for HPC, for desktop computing, for a whole range of use cases, and a lot of those were not particularly well suited to cloud usage. Things like, for example, SMT, simultaneous multi-threading, was started so that you could run multiple processes or multiple independent processes on the same core. That's not going to work particularly well if you're renting a core and somebody else is running something on the same core as you, right? And you end up having a knock-on effect on your workload. So why would you care? Why is Ampere interesting for you? Well, it's first of all good for your pocket, right? If you look across all of the cloud service providers, typically the ARM64 CPU is the cheapest one available. There are a few reasons for that. We're giving you more cores per socket, which means that you have less real estate to build to house them, right? It's cheaper to operate, and you have more cores in a rack. So that means that those CSPs, even though the CPUs themselves or the systems are the same or similar price to an x86 system, you're only taking a small part of it, so you get those, your core minutes are cheaper. So that's the first big benefit is we've seen customers using Ampere CPUs for all of their cloud workloads, whether it's video conferencing or ride share applications, running high volume applications, and they're saving 20 to 30% on their cloud spend. It's a significant saving. But it's not just good for your pocket or good for your applications, it's also good for the planet, right? We're using less power. Power, I think we can all agree at this point, is the constraint of future cloud growth with AI and so on. We're hitting the limits of what the grid can do, and we've already hit those limits in some areas. There are urban regions around Europe that are not building houses because there's too much strain being put on the power grid by data centers. That's the case in the Netherlands, in the UK. Right now, Ireland, my country, over 20% of all of the electricity generated in Ireland is being spent on data centers. It's kind of unsustainable in terms of its trajectory. So it's not an abstract concern. Okay, so there are some really good reasons why you might want to embrace ARM64 for your cloud workloads, right? Already price, but also lowering the power and operating expenditure if you're running them in your own data centers. But I think there's concern about how much work might be involved in making that move. It's not a trivial change. It's not, just moving a binary and running it on a different machine. You have to think about recompiling all of your applications. You need to make sure that all of the software and dependencies that you care about are available on the architecture, and we'll get into all of that. But before that, I want to talk a little bit about how the cloud changed the way we build software and the way we build and deploy software. The cloud fundamentally changed the way application development happened. I don't think this is a cloud native day, so I'm preaching to the choir here, but allow me a little latitude. 20 years ago, we were in 3-tier architecture. You had your middleware server that the way you added capacity is you added more disks, you added more memory, you added more CPUs. You had your database with your DBA on staff, and the way you added sizes, more disk, more memory, more CPUs. So you had these big monolithic servers that were running large workloads, and that was the way we scaled. And the cloud fundamentally changed that architecture. Cloud scale requires automation by default. If you're deploying something to a cloud and you're deploying hundreds of VMs or thousands of containers, you need to be configuring those things independently of, you can't do it onesies and twosies. You need to have some way of doing that at scale. So automation was one of the big changes that was driven, from 2006, 2007. It's been driven all the way through to now. And cloud economics incentivize scaling components on demand. You don't want to pay for something that you've provisioned for 1,000 users per minute when you're getting 10 users per minute. You also don't want your application to fall over if you go from 10 users per minute to 50 users per minute, right? So scaling components independently based on their needs is important. So we break apart that monolith, right? We're no longer provisioning for maximum demand. We're provisioning for end-to-end service time, in fact, right? But that adds a lot of requirements, right? You've got hundreds or thousands of compute elements. You need to know what's happening in each of them. You need to be able to identify if there's bottlenecks as they come up. So this is the architecture. Now let's talk a little bit about a specific example. This is one component from Uber. So I've got a new pair of glasses. I'm going to ask for your indulgence. I got a new pair of progressives, and so I don't know if any of you have progressive lenses. But so you've got a different lens on the top and on the bottom of your glasses. So if you want to look at something that's like 24 inches away, you need to have to find exactly the right spot. So I'm having a hard time with it. So I took them off for this presentation. So that's blurry. This is clear. We're going to be good. But so if I look at this, this is an Uber application. Uber is the kind of an application where you've got hundreds of services, and each one has their own components. Microservices in general, you want different teams to be able to work on their microservice without impacting other teams. They're developed, updated, scaled independently. Everybody gets their own data store. You try and share as little information as possible. All communication is across message bus or some kind of asynchronous communication of intent. So architecture becomes a little more sophisticated. Individual components themselves become simpler, right? You end up having a single service. Looks like, request comes in, I do a thing, I verify the state of the system, I make the change to the state that's requested, I send a message saying that the update has happened. So each service, even though it's simple in itself, has separate components. It's going to have its own storage, it's going to have its own caching, it's going to have its own packaging, testing, maintaining consistency. You define the APIs, you define the communication mechanism for talking to it and what you expect in return. But the application itself is going to be multiple components. So an individual microservice might be a single VM, but it might consist of independently scaling data store, cache, and application components. So we need a way to be able to do all of this updating and modifying things independently and make sure that we don't break anything. And that's where continuous deployment or continuous delivery became kind of a standard delivery pattern for microservice applications, right? Humble, Jeb Humble? I should remember the name. So the idea of continuous deployment is, again, the cloud driving automation. You need to be able to define what a compute node looks like in terms of intent and say, these are the capabilities I require of this compute node, and then I need to be able to deliver software to that compute node that has those capabilities and monitor and integrate that into my service. So we separate the building of the application and the packaging of the application from the building of the compute node that it's going to be delivered on. That's the essential pattern of the continuous deployment, is you're going to hold host definition in a different repository to your source code, and you're going to dynamically build the compute nodes that your application is going to run on. So we just walked through an example of one of thousands of microservices. How they get deployed is essentially, now I'm reading, which is a bad pattern. I think I covered all this information already. Okay, so what does it look like when you're actually building a cloud application? Well, starting at the build stage, somebody commits a change to a source code repository. That's going to kick off your continuous integration process, right? You're going to kick off a build. That's going to build and package your software. Maybe you have a gating test before you even get to that, right? That you're going to verify that the source code passes some standard conditions. So your automated build is triggered. To build for a specific target architecture, you've got to provision a build environment. Then you do your build. Then you package for your test environment. Then you've got to provision a test environment. You deploy your package into that test environment. Then you run the test suites, the functional test suites, the integration tests, the performance and load tests that you want to run before that gets to deploying to production. Once you've passed all of those gating tests, then your application goes into a deployment phase. You provision a production environment that's going to be different from your test environment, different from your build environment. And then you decide what the deployment pattern looks like. Are you going to incrementally migrate everything and use some kind of a canary method where you're deploying just 2% of your install base? You run your tests on the 2%, you see if it's better or worse, and then you go next step, you go up to 10%, up to 50%, whatever. Or are you going to do a green-blue model where you deploy an entire deployment of your application, run that test against production scale, and then flip the switch in your network or your service mesh or whatever you're using to manage how traffic is routed into your application? Or do you do something like a test deployment where you're deploying just a percentage, you do run some kind of test to see how a change operates on a small percentage of your traffic? All of these are deployment patterns that you can codify in your deployment, in your GitOps or continuous delivery infrastructure. And all of the boxes that are darker here, those are the ones that change when you add a new architecture for your build and deployment process, right? So if you're provisioning a build environment and your provisioning scripts are for x86, you're going to need to make sure that you're provisioning an ARM64 instance. You're going to need to make sure that you're doing so, that is tested and working. That requires some work. On building, you're going to need to make sure that all of your build dependencies and all of your build tools work well on ARM64, that you're doing all the build. Same thing with packaging. Same thing with provisioning test environments. All your tests are going to run on a different architecture, so you're going to need to make sure that they work on the new architecture, etc. So there is some work involved. It's not zero effort to add a new architecture. Okay, I don't want to go into too much detail, but again, in this room, who here is using Argo or is familiar with GitOps as a deployment pattern? Okay, so I'm preaching to the choir. The general idea of GitOps is, I commit a change into a Git repository. That commit triggers a build and test cycle. Then I push the new container that I've built into a repository that's for a deployment. That triggers a That updates an application manifest that triggers a deployment, and my application gets updated. That's the general idea. So I'm connecting a Git repository in which my deployment artifacts are going to be deployed. I'm connecting that to a Kubernetes cluster that watches for changes and does the deployments that I want. Again, I went super fast, and that was high level, and I skipped bits, but you all know what GitOps is, so I'm not going to explain it again, worse. But here's how the actual practice of doing your your multi-architecture build, here are all the steps that are actually involved. And so this is the meat of the talk. I think I know we have an hour, but I think I've scheduled for like 40 minutes, 45 minutes. I'm going to try and keep this interactive. But it's kind of a layer cake, right? There's lots of technologies involved. It's one of the things that's kind of challenging, but there are only a couple that actually care about the underlying hardware architecture, so hopefully that makes it a little bit easier. You know, you got to figure out how to build ARM64 containers, so you got to understand, you know, how to do that with Docker, Podman, Builda, whatever you're using. Then you've got the container repository. They're just shipping binary objects. They don't care what the architecture is underneath so Docker Hub or Quay or whatever you're using. They don't care what the binary is. It's tagged and you query and get and whatever. Then you've got your Kubernetes YAML. You need to know what's involved in deploying that image to a cluster. You're going to need to know like how to create compute nodes for different architectures, how to add those to your Kubernetes cluster, and then how to actually deploy to those nodes in your Kubernetes YAML. Application manifests themselves, this is how we do, for Helm operators customized. When you've got multiple containers that are part of an application, you can manage the application lifecycle with these. And then finally, we've got the GitOps operators, which actually don't care about architecture either. They just sort of, they're following a recipe, right? So the main bits where there's work to be done are in getting your containers building for ARM64, creating multi-architecture manifests so that when you pull a manifest, it picks the right architecture among multiple, and then actually doing the orchestration, figuring out how traffic is going to flow across x86, ARM64. Do you want to have fallback to x86 if there are no ARM64 nodes available, that kind of thing. So it's the application lifecycle part, and then actually the building containers and building your software part. Software upgrade available? That's annoying. Is there a new version of Fedora that came? No, it's just updates. Okay, so we're going to talk about just layers 1 and 2. What's involved in building multi-architecture containers? So who here has built ARM64 containers? Okay, container manifests, obviously the same people, okay. So binaries are binaries. They're built for operating system and then built for execution format like ELF or whatever. I don't know. I don't even remember what was before ELF. And then they're built for an architecture, right? They get translated into machine code, so they need to work for the target architecture that you're going to build on. And obviously, you know, a container-based image is a collection of binaries, right? It's already been compiled for that architecture that you care about. So first step is you need all of your binaries. If you're building binary objects, you need those binaries to be compiled for every architecture that you're going to deploy to. And the way that happens in general is my recommendation, I guess, is you can independently build containers that are for the target architectures that you're using. And there are a few ways you can do that. We get to it on the next slide. And then you create a manifest file which just lists the SHAs for each of these containers with the tags associated with them for example, platform in this case. And then when somebody does a Docker pull or a Podman pull, it is right, yeah, of that container, if they pull the manifest, what it does is it says, oh, you're running on ARM64, let's go pull the ARM64 image. So you can do in a single step with Docker build-x or Podman build-x. You can build all of your architectures. If you do that without having, I'm jumping ahead of myself. The normal way you do that, the normal way you build a multi-architecture manifest is you build for each platform that you're targeting, you push those images, then you build your manifest, and you push the manifest. That is the easiest way to get this done. It's the way that fits most into CI processes. You can also use Docker BuildX or similar to build all of the architectures in one go. You just give it a list of architectures, and it goes and it builds them for each one. If you don't have build nodes defined in Docker, and there's a way that you can say, I want to use different build nodes, so if I want to do native builds for every architecture, but if you haven't done that, it's going to do it in QEMU or something, and it's going to take forever because you're emulating a hardware level. It's not a good idea. I do not recommend that you do that. Okay, so this is where you're going to need to modify your CI to ensure that you have ARM64 build nodes, that they're being used to build the software, that you're actually integrating the, building the manifest into your, it's a new step that you need to add to your GitHub Actions or whatever you're using. I would say there are a few best practices. First, I recommend that you build the images separately on native hardware rather than using QEMU and building them their own. That's a kind of a common theme. Be very careful of tagging. I don't know if anyone here has had this issue, but in a text file defining manifests, Linux/AMD64 looks really close to Linux/ARM64. I don't know if I'm the only one who's lost a few hours with that, like looking at manifest files with that. And yes, be careful of tagging. I would not, so there are a number of times where I've pulled what I thought was a manifest, like without a tag, it's just, it's just got a version tag, it doesn't have an architecture tag. And what somebody had done is overwritten a manifest with an x86 binary. So this is in terms of if you're using Quay repository or Docker Hub, be very careful that when you're writing Docker images, that you're writing them to the architecture version and not the manifest. One of these like little steps that you hit along the way. Okay, so this is the one that everybody here knows, right? I'm not even going to ask. This is the Kubernetes part, right? We're going to talk a little bit about what a typical Kubernetes application looks like. You're going to have multiple services with components in there. Some of those components might have secrets or config maps. And you've got some kind of compute component, right? Pod, deployment, replica set. And then you've got, as our previous speaker was talking about, ingress, where you've got your network comes in, you figure out how to communicate to the right port, and et cetera, et cetera. So I want to talk a little bit about the compute part, right? The deployments versus replica sets in particular. So I'm not even going to ask. Okay, so this is not a trick question. This is the first question of 3, so we're going to go through this one quickly. This is some YAML. It's a replica set, name test RS replica set. We're going to create 2 replicas of a spec that has containers, name hello world, image nginx 126. After I run this, what am I going to have? Not a trick question. Faisal? 2 containers. 2 containers of nginx 126, right? Okay. That is correct. That is not a trick question, as I said, right? Okay, here's where maybe it becomes a trick question. If I change that same YAML file and I go to replicas 4, and this time I want image nginx latest, right? I apply this. What do I have? Anyone want to take a guess? Put a hand up. Okay, so we've got one person, Faisal. He says we have 2 latest images and 2 with the 126. Who thinks we have something different? No, it's still not a trick question. That's the answer. Good job. So the important thing here is if you're using replica sets, they are imperative, right? Which means that at a point where an event happens, in this case, we apply something that says replicas 4, it's going to look at the label, and it's going to make sure that we have 4 containers with that label running. And it sees that we already have 2 running. It actually doesn't care what those containers are. It leaves them alone, and it just starts 2 more. That's one of the big differences between a replica set and a deployment. Okay, part 3, and this is still not a trick question, probably for this audience, a bit elementary, but okay. What is running after this? Okay, so I look at the pods I have running. I've got 2 Nginx 126. I've got 2 Nginx latest. And I decide to delete one of the 4. By the name of the pod, I delete one of the 2 Nginx 126 images. What do I have running after this? Sorry? 3 latest, indeed, yeah. So what happens is, once I stop the pod, the replica set notices that I only have 3 running. I'm not matching with the replicas, so it starts a new container with the image template that's defined in the replica set. So replica sets care about the number of containers that are running with that label. They don't care that those containers are all running the image that you define. Deployments, on the other hand, do care about the images that you specify in the template. So replica sets just ensure that a certain number of containers with a given label are running. Deployments manage replica sets. So a deployment, when you upgrade to a new deployment, will create a new replica set, and it will apply various rules to kill containers in the first replica set and start containers of the new image, of the new template in the second replica set. So they come with, again, this is probably, like, has anybody here learned anything yet? Oh, okay, thank you. I was looking for reassurance. Yes, it does, yes. But not everybody who uses Kubernetes has read Kubernetes documentation, Faisal. And deployments come with 2 important parameters. One is max surge. That's how many new containers you create above the target number of replicas in the new replica set before you start, before it stops creating new ones. And then max unavailable. So the way a rolling update works when you apply a new deployment is you create a new replica set, and it starts to create containers with the new template. When some of those containers get to running state, it starts to delete some of the containers in the old replica set, and it continues along that way. It'll start more on the new and delete more on the old until it gets to a point where you've got all of your replicas are running in the new replica set. So these 2 parameters, max surge, that's how many new ones you attempt to create before you say, okay, this isn't working. And max unavailable is how many you kill in the old one before you say, okay, we're running short on resources. And those are the important parameters that you're going to see when you're deploying it to a new architecture. This is one of the ways that you manage, is this thing working on the new architecture? Okay. Workload placement. There are 3 essential ways that you can do workload placement in Kubernetes. So obviously, the workload placement, pardon me? Okay. The workload placement is fundamental. It's really important if what you're doing is deploying to a new architecture. So you use labels to mark nodes with a certain capability or restriction or just random text, right? It's just text. But you select, you can use the node selector method to force workload placement on nodes with that label. So that would be a good way to say, I need a GPU instance, I need an SSD, whatever it is. Another way to do it is with taints and tolerations. So you taint compute nodes. You say this compute node is of this type. It has been tainted with this label. And then in your pod deployment templates, you say, I tolerate, I can be deployed on pods of this type. And I believe the tolerations, and I could be wrong here, I believe the tolerations can be either requirements or suggestions, like preferences. And you can fall back to something else. But the one that definitely, okay, so taints can be used to prevent scheduling on things like memory pressure, disk pressure, and taints can both prevent new workloads or they can force the eviction of workloads to other nodes. And it helps Kubernetes identify which nodes are prioritized to be evicted. If, for example, you end up on memory pressure, you can say, okay, this one doesn't matter so much, I'll just kick it off to something else. This one really needs this function, this capability that I have on this node. Nodes can be tainted with a scheduling restriction. So, for example, reserved for certain workloads or with special hardware. Pods can have tolerations indicating that they require or prefer. Oh yeah, so it does have require or prefer certain capabilities. But my favorite is affinities, right? So node affinities are similar to node selector, but it's a little bit more complicated. You've got a little bit more nuance in how you define them. You can have required or preferred characteristics, and you can have those characteristics apply at startup or during execution. So for example, when a node gets to a certain, if a node is being shut down, right, what happens to that workload? In particular, we use node affinity for the architecture. So this is small up here, but well, that's terrible. I don't know what happened there. I think I know what happened there. So I was in presenter mode, and I guess whatever. This is a virtual keyboard when you. I mean. We'll go with that. And I guess I will not use the red pointer again. Sorry about this, folks. Okay, we're in the right general neighborhood. Okay, so in this case, we've got a template, we've got a spec where we've set our node affinity to have it required during scheduling, ignored during execution, and our node selector terms are we're going to make sure that pods created with this template are going to be they can be deployed onto ARM64 or AMD64, with the preference being the first one, ARM64. Simple as that. Okay, so we're going to get to an example later, but layer 4 Helm charts, I'm not going to spend a lot of time on this because Helm charts are basically just Kubernetes YAML files with some templating to allow you to do kind of namespace specific stuff or some modifications specific to a specific cluster or namespace that you're deploying to. It's more than that, but there's not a lot to do in terms of the architecture. All of that is already in the Kubernetes YAML. And then we get to the last bit that kind of matters, which is ArgoCD GitOps for Kubernetes. So who here has used ArgoCD? Yay. Okay, so Argo's great. It really is. Okay. So Argo essentially ties your Kubernetes cluster to a Git repository. Simple as that. You've got, you create a context. So you get a context from a cluster. You add that cluster context to ArgoCD. ArgoCD cluster, add cluster name, and then create app name, and you connect it to No, So you get your context and you connect your context to your Git repository. I think I've messed up the commands here. I don't think I copied them right. But once you've done that, what you've done is you've created an application that's going to connect the context to the Git repository, and then when something gets committed to the Git repository, you decide what happens. So ArgoCD is automatically going to detect if the Git repository is out of sync with the application, and you get to decide, oh, I'm going to do a manual rollout. I can have an automated rollout. I can have rollouts be dependent on acceptance tests. I can define whether those rollouts are incremental and what the gating is for going to the next step. There's a bunch of stuff that you can do. And one of the things that I really like about Argo is that it basically codifies some of those deployment patterns I was talking about earlier, blue-green, canary, A/B testing. It gives you the ability to run those without having to manually update the service for your application or your cluster. So again, Argo rollouts. So Argo rollouts are different from ArgoCD. Who has used Argo rollouts? This is the one that does the deployment patterns. So it's custom CRD for managing deployment rollouts. You basically say, I want to do this deployment with, canary or blue-green or whatever. I really like Argo rollouts. I think, and I think it's the best way to do multi-architecture applications because it gives you the ability to have that, one of the things that we talked about earlier is sometimes people push containers that they're supposed to be multi-arch manifests and they're actually x86. You don't break stuff if you deploy that by accident. So the way the blue-green deployments worked, at least for me, before Argo rollouts is I have an ingress, which I think everybody had to change recently because of the Nginx ingress controller being end-of-lifed, but we're not going to talk about that too much. So I start with my ingress pointing entirely to the blue service. My blue service is like just managing the front end, let's say, of my application. I start a green deployment, and then I update my ingress to point to the green deployment. So I have one ingress that's basically doing the juxtaposition, doing I have notes here, which I can't remember, which is not the best place. Okay, so the green deployment, we have to make sure it's complete. I'm going to move on. And then once we've got our green deployment working, once we've changed the ingress to point to the green deployment, then we scale our blue deployment to 0. So it's a lot of manual steps, is the point. If you're doing this with blue-green deployments with Argo rollouts, you've got a single ingress point that's pointing to a service that's managed by Argo rollouts, and then the rollout itself manages the blue replica set and the green replica set, and does that change of service for you. So it's a one-step thing. You set your image rollout to green. It basically completes the process on its own and then tells you when it's done, and then you're done. You move on with your life. Similarly, with canary deployments with Argo rollouts, you basically configure your ingress. So you've got the two replica sets are managed by Argo. You say, I'm sending n% of my traffic to the new, to the green. I can have acceptance tests that run. I can run as complicated of tests as I would like to run for functional tests to gauge at that point whether I want to go on to the next. I can have a manual step to approve to go to the next step in the process, or I can have it be automated based on test results. And this is all managed within Argo. And if you're moving an AMD64 to an ARM64 application with Argo rollouts, using Argo, you basically just have your affinity in the template. You say, okay, I'm going to change my Kubernetes, my node affinity from Kubernetes Arch AMD64. I'm going to change it to ARM64. And that change there, I know it's tiny text and small screen. And that's, and you're done, right? That's the point. It's kind of a punchline. Once you do this, once you just commit this change to the Kubernetes YAML and you deploy the new Argo version, and if you're using something where the application is available as a multi-arch manifest, you have nothing else to do. That's kind of the point. I'm sorry, I'm a little flustered. I am ready to take questions. Rotten apples, eggs.
Pretty good. Thank you.
Thank you. We do have a lot of developer resources on Ampere Computing. You can go along to some of these QR codes, and we would be happy to see you if you are an expert in managing multi-arch containers in our Ampere developer community. Look forward to seeing you there.
Thank you. I wonder if you know of anything like Argo rollouts that works for daemon sets.
That works for?
Daemon sets.
I can't hear the...
Daemon sets.
Daemon sets. I do not. Does anybody here know something similar to Argo rollouts that works for daemon sets? Or daemon sets? I'm sorry, I'm not the right person to ask. Thank you.
All right.
You mentioned Flux before. Is
Yep.
Flux just an alternative, or does it built on top of Argo?
Oh, it's a completely different GitOps system. So Flux was developed by somebody called Alexis Richardson. By Weaveworks, yes. So it was an alternative, and yes, now it's like a community-run open source project. It's the same idea. You connect a Git repository to a Kubernetes cluster, and it monitors the deployments for you.
Right.
But it's a completely different implementation.
The other thing I was curious about is for people that, this seems like, well, I'm going to assume you're managing your own Kubernetes.
I like to use managed Kubernetes. If I can avoid running my own Kubernetes cluster, I'm happier to.
Okay. So these things are all applicable if you use EK.
Yeah, if you're using like OKE or GKE or AKS or EKS, you can run your own Kubernetes cluster. And the one thing I didn't touch on that I probably should have is what's involved in adding ARM64 compute nodes. Right, so you can create node sets. I think they're node pools is the language that's used in sorry? I was not going to talk about Carpenter, but so you create a new node pool. At least the way it works on OCI, which is the one I'm most familiar with, is you create a new node pool and you say, I'm going to create so many compute instances with this many CPUs, or like you choose your instance type, and you say, I'm going to create nodes in this node pool that are ARM64 nodes, and then there's a certain amount of metadata that's automatically set in the Kubernetes space, like architecture equals ARM64 is automatically set. You don't have to set that, but you can also tag those nodes with, for example, let's say you want to run a 64K kernel, which is something you can do with ARM64 that you can't do with x86. Well, then you would start your instances with a 64K kernel, that you would have to make that image available so that you can do that. And then you tag those, this is an ARM64, but 64K kernel, and then you can use the scheduling rules, node affinity, to make sure that you're running things that benefit from that.
Right, thank you.
So that, yeah, every single hosted Kubernetes has that capability of creating those node pools. And you can do it with self-hosted as well if you prefer like a Kubernetes or like a Kind or a K3S or OpenShift, whatever you use.
Any other questions?
Well, thank you all for your time today. I hope this was useful to you. I know it's always dangerous coming to a cloud native event. Everybody knows Kubernetes. But I hope you all learned something. So, thank you very much.
Hi.
Okay, it looks like it is the start time. Welcome to the Cloud Native track at the SCaLE conference. We've got a great presentation coming up on change-driven architecture with Alan Jones. Alan would like it if you could hold questions until the end, and he's going to introduce himself, so take it away.
Thanks. Evening, everyone. Thanks for coming. Thanks for being the last 10 people at the conference for the day. all credit for making it to the end. My name is Alan Jones. I work for in the Azure Incubations team at Microsoft as an engineering manager. Our team produces and releases cloud infrastructure software. Some of the software that has been released from the team, things like CADA, Dapper, which some of you may be familiar with. And today I'm here to talk to you about one of the newer projects that we've released that I manage called Drasi. And Drasi means action in Greek. Drasi was started because of this problem, that detecting and reacting to change, particularly in data, is harder than it should be. And it's probably familiar to people in this room that the situation you have multiple systems, data spread across them, data changes. You want to do something about it, right? You want your system to react. And you want it to be quick and precise, and you want it to be reliable. So, some examples. This one is, proactive customer care. So, a shipping partner marks a delivery as it's going to be late, it's going to be delayed. You want to go through your customer relationship system, your order system, look at who's got an order that depends on that delivery, figure out who's affected, figure out of who's affected, who you actually care about in terms of keeping their loyalty, and go and offer them something to sort of sweeten the fact that their order's going to be late. Right? Systems are reacting to the fact that this has changed to allow you to improve your service to your customers. Another example, if you're managing a field support team, you've got tickets coming in. There might be specialist training needed for a high priority ticket. You've got these field agents out. You sort of know where they are, but getting them to the right place at the right time when there's a high ticket and they're available, it involves lots of moving parts. So you can optimize that if you have a mechanism that can respond to all of those changes coming in: location, tickets, priorities, training, all of that firing off together to tell you who's close to that ticket that you can send. And last example I'll touch on is sort of a more modern one. Customers calling in with an issue about a missing order. They either talk to a customer support engineer who's using an AI agent, or they talk directly to an AI agent. And the AI agent looks at the information it's got available to it, which was last refreshed overnight, and confidently tells the customer that the wrong information, right? So if you had a way of, when information that was entered into your system immediately got fed into the vector database that this AI agent was using, you could have told them the right information. So hopefully you get a sense from those examples the kind of thing we're talking about. And we call these change-driven systems. And these are systems that take action in response to specific meaningful changes or the absence of change, which we'll talk about later, in relevant data. And as we go through this is probably a problem that you guys have already all solved, probably more than once. So we're hoping that we can solve it for good. Now we're going to jump into an actual working example of what we consider to be a change-driven system. And I'm going to use the example of a trading application that we'll use again later on. But I just want to make sure everyone's sort of got that sense for, things are changing dynamically and things need to be updated. So many of you have probably done some trading, you've got some market data systems. But if you think about a trading application, there's market data coming in, you want to manage a stock portfolio, so you've got a set of stocks, you want the prices to be updating, you want to be looking at the P&L of the portfolio. You want to be trading, so you're going to put in orders. You might want to do limit orders, so you want to know when these orders have filled, when they've cancelled, when they've expired. You might want to watch certain stocks, so you configure stock lists, and there's prices coming into those. So we can imagine that there's multiple systems feeding into this trading application, including like order management system, stock, portfolio, watch list tracking, and market data. So this is a live working example and we'll dig into this a little bit more, but fundamentally what's happening behind the scenes is there's a price feed coming in, and it's updating the prices of certain stocks. There's a database that has your portfolio in. There's a database that contains your watch lists, so that the kinds of selections you've made, the kind of things you own, and then there's a system for doing ordering. But as a stock price comes in, many things might want to be updated, right? So if it's in your portfolio, you want your portfolio to update. If it's also in your watch list, that needs to update. So one change can result in many updates that you want to be doing, okay? Now, the examples I'm going to be talking about moving forward are very much focused around this idea of UI changes and updates. But Drasi's not just about, it's not a UI technology. It's just good for presentations and visuals. So knowing that those changes coming in have to affect maybe so many things, you can't just wire that app up to all those systems. You're going to have to build something. And so you start thinking about, well, how do I get the changes from those source systems? How do I get them into my system? Like, what is the feed mechanism? How do I retrieve that data? How do I integrate that data across multiple sources in real time so I can get those meaningful insights and results? How do I update all the dependencies for the system? How do I get it from the system, whatever that system is, out to the application, out to the UI, that last mile? So if this is the first time you guys have sort of thought about building this kind of system, you had to do it, you're probably thinking, oh no. And if you've done this before, you're probably thinking, oh no, not again, right? So there's a lot of repetition, and we've probably all been in situations where we want to react to changing data. So how do we build change-driven systems today? There are three common approaches that we see in the customers, the partners we talk to, and also that we've used. We are guilty of using these techniques, and sometimes they're fine, and you use them, and you've got no choice. But we hope to do something better. So if we look at these, approach one is, it's the go-to. Like, this is when you want to update some data, realize when something's changed. The first thing people tend to go to is, oh, I'm going to poll it. It's fine. I'll just poll the database. So, with this, you've got some process. It's going to periodically query the database, get some results. It's going to compare those results to the previous time it did it, figure out what changed, do something. Right? So you write that system. But I saw this quote that I quite liked. It's like opening the refrigerator every 5 seconds to see if new food has arrived. Okay. So approach two, less common, but if you've got it, people are going to try and use it. So if they've built out an analytics platform capability, bringing all that data together, it's already in one place, it's already in this unified format. It's like, why can't we just detect if that's changed? And so people start to build jobs on top of it that then kick off processes, that then kick off events that trigger downstream systems. And yeah, it does work. And if you're not too worried about the timeliness of your change activating some process, then it might be okay. But again, there are certain downsides to that. And the third sort of option we see very often, particularly in larger organizations, is the use of event stream processing. So, they've got databases, they set up a CDC system, it feeds into some Kafka streams, they've got stream processes, they've got custom jobs, these detect changes, they're managing the state, boom, they've got a change, and out it goes to the consumer app. This is great. But it's also, a lot of work and beyond the capabilities of a lot of companies. So all of those three introduce significant complexity for both development and operations. And they make you focus on plumbing instead of on producing business solutions, right? And they often result in these one-off brittle solutions that inevitably become issues down the road. So that's common to all of them. Each of them has their own quirks and flaws, listed here. I won't go through them all, but polling is quite wasteful, and there's this immediate trade-off of polling interval versus recency, right? So you need to make that trade-off. It doesn't scale, so if your data's very large, that whole poll thing can be quite an overhead. If you have one of these systems, yeah, it's maybe okay. If you have two, probably okay. If you have 50 of these things going on across your organization, it's not good, right? The analytics platform, you're not going to spin up an analytics platform to do change detection. So you already need to have one, most likely. So it's cost prohibitive to actually use this unless you've already got it. There's the ETL lag, so whatever the timing is on your ETL into the system, that's going to dictate how quickly your events can be detected. And the event streaming, it gives the fastest, most realistic sort of answer to change detection, but it's heavyweight. Right? There's a lot of moving parts, there's a lot of technology. Going down that route is a lot of effort to commit your engineering and your DevOps teams to. When all you really want to know is, has something changed? Right? That's all I want to know. So there has to be an easier way. And what we really want is something that has these properties. It's purposely built to just do change detection, to just help you build change-driven architectures. It's easy to use. Because it's doing one thing repeatably, you can sort of deliver it to have no-code, low-code, full-code options. It combines the idea of, I want to detect change and then I want to do this with it. So combining that detect and react with minimal infrastructure and integrating the data, wherever it may be, for the purpose of solving that problem. And also a rich ecosystem of connectors to get it to the data to get data from where the systems you want and to places that you want. And of course, we want it to be open source, community driven, and without vendor lock-in. Believe it or not, Drasi is the answer. So what is Drasi? It is a data change processing platform for building change-driven solutions. It is open source. It is released under the Apache 2 license, and it's already in the CNCF sandbox. So it is available today. You can go and play with it. Core concepts. These three very, very simple concepts at the heart of everything to do with Drasi. Sources, continuous queries, and reactions. Sources are the things that represent the data sources that you are connecting to and bringing data from. You've got your continuous queries in the middle, and the reactions represent what you want to do to act on those changes. That can be integration with downstream systems or do some bespoke logic that is a particular action. So we'll go through those in a little bit more detail. So first, sources. These are responsible for managing the connection to a external source. It could be we'll go through them in a minute, but it's not just databases. There are other sources you can connect to. It receives or retrieves the changes that are occurring in that source. And ideally, that's from like a change feed, but we have done certain sources that don't have access to a change feed. So some sources mimic, through those nasty mechanisms that we talked about before, but they keep it hidden from you so you don't have to implement it. But ideally, we come from a change feed. So we don't put load on your database. The source is responsible for transforming that inbound format from whatever feed it's processing, transforming it into a consistent property graph node relationship model that we use internally that we do our graph queries over. And then it's done that transformation, and it sends what we call a source change event to any queries that are subscribed to it. So you can see down the bottom here, we've got multiple sources active. They come into a source, multiple data sources active, come into a source. It gets turned into this source change event. If you're familiar with the Debezium formats, it's very similar. So within it, it talks about what's been inserted and updated and deleted. and then it eventually gets to the continuous queries that want to subscribe to that source. So we already have a fairly rich ecosystem of sources available. So we support relational data, Postgres, MySQL, SQL Server. We support graph and document databases, so Cosmos, Dataverse, Kubernetes. We treat it as like a document graph type database for its internal configuration. And stream systems. So we started this project focusing on databases. We started actually focusing on graph databases, the ones we talked about there. And then it was like, hey, let's integrate relational databases. And now it's like, okay, let's integrate stream sources. So event hubs, HTTP, gRPC. And also, there's a full SDK with tutorials with which you can write your own sources. Also, we are just working on an AI agent that we've had a lot of success with, that you tell it the source you want to connect to, point it at its source documentation, it will go off and generate a full source implementation for you. It's pretty good. We're still knocking off the rough edges, but we've had some really good fun with that. And it makes it super easy to get a first draft of a source. All right. Sources have got the data in, pushed it, made it available. Continuous queries are next. They get the data. They subscribe to one or more sources. So it can be subscribing to many sources of different types to use in a single query. And this is one of the unique features of Drasi, that it makes that really easy to do. The queries are written in OpenCipher or GQL, so they're both graph languages. We have done an experimental SQL implementation, but it's not something that we've decided to pursue for the time being. And what it does is you've got this query, this continuous query running, and the secret is in the name. It's continuous, so it's taking each change and figuring out how that change that it's got from a source has affected the result set. Right? So it will maintain a perpetually accurate result set based on all the inbound changes that it's getting. So if you were to ask it at any point, what is the current result set, it would be accurate based on the last inbound event it received. Then so it's managing that. Internally, it's got a set of indexes to manage the elements that it needs. It manages aggregations, we'll talk about that in a little bit. It manages the current result set, and it figures out the diffs, and it sends it off to all the subscribed reactions. And the thing that makes this workable is because we've now turned this notion of a change into a semantically rigorous structure. Right? So anyone that receives that knows, oh, if this contains something that was added, well, it's been added to that result set. Therefore, it's now part of that set of things that I was interested in, right? So, some examples. And these are just going to be like simple queries. So if you're familiar with it. This is a Cypher query. So I said that we model everything as a property graph. We support GQL and Cypher. So the match is sort of saying, I'm interested in stock prices. So if the data is coming from a graph source, it's going to have a node label called stock price. If it's coming from a relational database, it's going to be from the table stock price. Right? So each row in a relational table is a node in our property model. So this query is interested in all stock prices that it sees. And then it's just going to return a projection from the stock price. It's going to return the symbol, the price, the previous close, which is straight out of the stock price record, and then it's going to do a calculation to turn out the change percent. So the result of this continuous query is going to look like that. And it's always going to look like that with slightly different data in, because as new stuff is coming in, it's going to update this. And if you ask it at any point in time, you're going to get that. Right? Perpetually accurate. Second example, a little bit more sophisticated. I'm interested in all stocks that have a price higher than yesterday's close. So again, top line, match. Here, we're saying we're interested in stocks that has a price to stock price. So we've got this relation. So has price is the label of the relation between those two nodes. And of course, if we're bringing data from a relational database, we just bring in the relations as they come. If we've got, graph database, if we bring in data from a relational database, we provide a mechanism for you to define synthetic joins between those things. We don't currently try to create those relations from foreign keys and all that kind of stuff. We want to keep it super simple. And I'll show you the syntax we use, but we allow you to create synthetic joins between those tables. And that's also the mechanism that you can use to join across multiple data sources. Right? So in this one, we've got this where clause, which makes this a little bit more selective than the previous. So here we're saying that the price today has to be higher than the price of the previous close. So this is going to reduce the set of elements. So we're not going to get all the prices. We're going to get the smaller subset of just those that have a higher price than yesterday. And again, we just project out some stuff from that. And its result set, if you asked it, would always be this. And every time it gets a change, it's going to update it, so it's perpetually accurate. Now so they're fairly simple queries, but they show that I can collect some data about a set of things I'm interested in. I can create a selection, a filter on that, so it's a reduced set. And then we also support the idea of aggregations. So this one, all market sectors. So I've got this matching of stocks that has a price to stock prices. So as part of the stock, it's got a sector associated with it. So in Cypher, any non-aggregating function gets pushed up and becomes the grouping key. Right? So in this one, we've got sector. It's the only one. So I'm returning the sector from the stock. So it's now going to group everything else by the sector. So I'm going to get the count of elements in there. I can get the average of the price. I'm going to get the sum of the volume, and I get the min and max price. So if I do this, I'm going to have a table that looks like this. And it will always look like that, and it will always be accurate. And being able to do these aggregations over continuous queries by just writing the query, you're not having to manage any of that historical state. You leave it to Drasi. It just handles it, and you write the queries that you want. All right, moving on from continuous queries to reactions. So reactions are what act. These are like the hands of Drasi. I saw something sort of say the other day. You subscribe to one or more reactions. Continuous queries. These receive from the continuous queries the result change notification, which is the set of things that's changed recently in the result set. And then they act based on that. And most reactions are built so that they handle added, updated, deleted changes differently. Right? So sometimes, for example, you might use one email template for things that have been added and another email template for things that have been deleted. All right? And when you write your reaction, you define that logic and how it's going to handle those changes. Ecosystem of reactions, we already have a bunch of reactions. So things that push data out into the world, we can push using webhooks, SSE, gRPC, SignalR, and we use SignalR for UI updating mechanisms, and I'll show you that in a minute. We have an ability to write straight back, so you can have a reaction that uses a stored procedure to update a database. So if things are added, updated, deleted, you can structure your commands, do something to a database. We do that with Postgres, MySQL, MS SQL, Gremlin, Quadrant. Integration type things. We have reactions that integrate with Debezium, Event Grid, Dapper, Grafana. And again, you can write your own. And again, we've got SDKs, tutorials, examples, and we've also got this AI agent that is also doing a fantastic job at writing initial cuts of reactions. So, quickly, very quickly. Okay, highly extensible. I've talked about a few extensibility points. Sources, reactions, bootstrap providers, so when a query starts in its initial data, state stores, index providers, like it's all pluggable. Middleware. So sometimes stuff's coming in from a source, the query needs it in a slightly different format, transformed, elevated elements. We've got a whole bunch of middleware that a query can define, and things that are coming into it will get pushed through this middleware pipeline before it has to figure out the changes to its query. So you can do quite complex, sophisticated things. Multi-source queries, talked about this. We can join across heterogeneous sources just by writing a query. Okay. Absence of change. This is a biggie because many systems, you can't do this very easily, right? How do you even begin to explain that something hasn't happened, right? So we have this way of writing queries that have some special functions that say, look in the future, and if something isn't true, then, fire off, right? And so we can build things that say, this was expected, but it hasn't happened, so we're going to, raise a notification. Some temporal functionality, things like, you can look back at the historical value of elements. You can look back at the result set at any point in time if you enable the temporal result store, which can be useful. And although I say this is not a UI technology, I always demonstrate the UI integration with Drasi because you can do something very cool, or what I think is very cool, and you'll see it soon and be able to judge yourself. But imagine a lot of applications are all about, I've got this set of things I need to show the consumer, the user. You can think about the set of things they're looking at, usually as a query result, right? The set of all customers that have overdue invoices. That's a set of things. I can tell Drasi to create that set of things, and then I can have it perpetually managed in the cloud, and I can basically data bind, a control in the UI to the cloud-based result set and keep it in sync. So, and I'll show you an example of that. Okay. Deployment options quickly. Drasi for Kubernetes. This used to be called Drasi Platform. It was the only thing we had. You need to deploy to Kubernetes. It can be in Azure, it can be in AWS, it can be on-premise. But it was pretty heavyweight, and a lot of customers were like, "Oh, I'd love to try it, but it's I don't want to build a Kubernetes cluster." Or we don't use Kubernetes. Like, how can I run it otherwise? So we've spent a bunch of time recently refactoring the whole of Drasi to offer this Drasi lib idea. So you can take the entire functionality of Drasi and stick it straight in your Rust application. So all the continuous queries, all the connectors, you can just embed it in your application and get all that power. Right? And then on top of that, we built a single process or Docker imageable host for Drasi lib. So now Drasi server is a standalone server that provides you all of this. You can get it up and running in minutes. Right? And it's a wrapper around Drasi lib that provides persistent configuration, a REST management API, et cetera, et cetera. So Drasi server is the best example of how to use Drasi lib if you're interested in having a look. All right, so let's get back into this example while we've got a little bit more time. All right, so coming back to that trading example, you've got all those things going off on the screen, all those updates coming through. This is what it would look like as a Drasi solution. So we're going to use Drasi server, and I'm going to show you this running. Inside Drasi server, we're going to have three sources, 2 to databases, and they're both Postgres, but they could be, one could be a MySQL or something else, but they're both Postgres for now. One database has orders, active orders, buy or sell. The other database has things like your portfolio, your watch lists, and the stocks, that are generally in a system. So changes to all of those things are going to come through those sources. And then we've got a price feed, which is mimicked by this background Python process, which is just spitting out price data into this HTTP source, right? So we've got this open HTTP source. The price generator is sending events, that are price events. These come into the query engine. I think we've got like 8 or 12 queries running. And then all of those queries are spitting out through this SSE reaction that the trading application that I'm going to show you is receiving all its data over. So it's receiving all its data through one connection to Drasi server through this SSE reaction. Now, just because it's a demo, there's some sort of short-circuiting going on. I'm going to be able to place orders and change my watch lists and this kind of stuff. You can imagine this happening in other systems or through other things. The trading app, for the purpose of the demo, is hitting this like little mini broker API that's going to directly update the database. So when you see me make a change in the UI, none of that state is being kept or updated locally. It's all round-tripping through the database and through Drasi. And then the Postgres reaction is down there because it's a Postgres stored proc reaction that doesn't exist on Drasi server yet. It's on Drasi platform or Drasi for Kubernetes. If it was there, I wouldn't need some little hacky things I've done to make this work. I could just be updating the database directly from here, and I could take some of these components out. So it'd be a much tighter loop. All right, so let's jump in. Here's this trading app again. Okay, so let me show you some things. Each of these panels is, you could imagine it as a query, right? So maybe this guy, my watch list. It's like, I want all the stocks that are on my watch list. And this is the query result. So each of these panels is actually effectively bound to a query that's running in Drasi server. And it's running locally, of course, but it could be running in the cloud. So, and this is an app we just used to demo. So it's got some features in that are just for the purpose of demoing. So you can see as the changes are coming in, we're highlighting the rows that change. So there's not a lot of changes necessarily coming into my watch list because I'm only looking at 3. But you can see in that full UI, there's a fair few changes coming in. But we can look at this, and if I expand this is showing me what query is behind or feeding this particular window or this panel. So you can see it's got an ID, the watch list query. Excuse me. It's a cipher query. It auto starts. Here's the query text. All right, this is the actual query that's running. So it's a pretty simple one. It's just doing this match between I've got this concept of a watch list node, and a stock is on the watch list, and then the stock has a price. So I'm now joining across 2 data sources here. 3 tables, 2 data sources. Well, 2 tables, 1 feed. And all of those, these relations, the on watch list and the has price, these are not coming from the source databases because they're not connected. So this is the sort of synthetic join syntax down here. So we let you specify for a particular node type or label, this property is going to match this property on this other label. And if that's true, we create this synthetic join between those 2 nodes, which let us do the mini graph walks to solve this query. It's just a direct match currently, but it can be extended to do some sort of manipulation to do compound keys or uppercase or prefacing or something like that. It can be added. We haven't done it because we've not needed it. So, so that's that query. If I look at another one, let's look at the sector performance. So we looked at this query earlier. Whoops. We looked at this query earlier in the examples. Yeah, it's called sector performance, cipher query. Here's the query, and we sort of talked about that. And here's my synthetic join. So again, once you learn this, you can create queries that connect all sorts of data, previously unconnected, and create these perpetually accurate queries, result sets. Now what's cool about this, I said everything's coming across this SSE feed into this web app. We've also created a component, and for our SignalR reaction and Drasi platform, or Drasi for Kubernetes, we've got a React component and a Vue component that are available, and they operate the same way. This is a React component that is written to take data from the server-side event, inbound mechanism. And so all you do is you say, I want to use the query table component, and I want to connect it to this query ID. I want to use these columns from the result set. And this whole user interface, this dynamic user interface, is effectively built by using that same panel again and again. There's absolutely no There's no state management code going on in SUI. So if I want to add something to my watch list, now I'm going to add this. It's going to go through that sort of janky little API that I spun up. It's going to update the database. I'm going to add Boeing. And like instantaneously, it went through the API, went into the database, came through the change feed from Postgres to its source, got processed, went to the continuous query, updated the query set. How do I know it updated the query? Because it appeared here. But I can also, in this screen, I can now go, and this is the Drasi server web UI. Now this is hot off the press, so there's some little quirks in it, but like no one outside of our team has ever seen this before. And so what this does, it shows you on the left, you've got your sources. These are all the continuous queries in the middle, and then this is the reaction out here on the right. So this is an SSC stream. I can click on these things. I can see what's connected. I can control everything. I can build new queries in here. I can create these systems. I can clone it, all that kind of stuff. So I can interact with it. Now we were looking at the watch list. So I can go down here and say, there's the watch list query. Let's expand it. Let's have a look at what's inside. And that's what's inside the query result at the time. Right? So it's a good tool for looking at what's going on, building out things, connecting them, trying them really fast, and seeing if it all works. Now, we've also got a VS Code plugin. So if you're into VS Code, it plugs in. It lets you do a lot of inspection about what queries are running, lets you deploy queries, et cetera, but it's not like this visual GUI thing. It's sort of, a click things and see trees and see data, but it's also very useful. Where are we for time? Okay, I'll show you. Okay, very good. So, now, let's go back to the UI for a second. Now, let's talk about these orders. So currently, there's four orders in this table of various status. Some are filled, some are expired. I'm going to place a new order. And this is the non-event stuff. I'm going to place an order, and nothing's going to happen. Now, I've got a query that says, after nothing happening to this order for half the time of expiry, set it to stale, set its status to stale. And then if I've got another query, which is any query that's reached its expiry time, expire it. Right? So change its status. So these let's look at those queries. So there's a stale order query. Right? So currently it's empty because there's no stale orders. It's loading. I don't know. I've never seen it before. Maybe it's because I'm not on the Wi-Fi. I don't know. The query would be in here. So what it's doing is it just sits there. There's no UI representation of the stale order query. It's sitting in the background in Drasi, watching orders to see if they've been not actioned for half the expiry time. Similarly, this one down here, the expiring orders, it does the same thing. And it does the same thing. Okay, so again, as I said, it looks for things that have expired and sets it and updates the status. So these are sort of workflow queries, right? So they're pushing this thing along through a state machine, if you will. Right, so let's go back and see this in action. So I'm going to add a limit order. Let's buy this. So we want just prices, random stuff. I'm going to say, it expires in 10 seconds. So I'm going to create the order. You're going to see it appear in that table immediately. So it's appeared, it's pending. So if we wait patiently, it went to stale, right? So the stale order, and now it's expired, right? So the order wasn't actioned. It stayed in a pending state too long. The query when it stayed in there too long, it appeared in the SCaLE order result set. That notified a process that I've got running in the background, which would have been the Postgres reaction, but we don't have it, so I sort of hooked something up. It then just writes back to the API, which writes to the database. It's gone from pending to stale. And then that process sits, the expiring query sits and waits. At some point in the future, it appears in there again and pushes it along. I wish I could show you those queries, but I cannot. I don't know why it's not loading. Okay. What else here? I think that's probably it. Okay, back to the deck. Okay, so why Drasi? We want Drasi to be the simplest and quickest way to create change-driven architectures. Why do we think we can achieve this? Because it's purpose-built for doing that one job. A query and some configuration replaces a whole wide set of infrastructure that is still, it's awesome for other jobs, but for this job, we want Drasi to be the best. It's simple in both its ability to be understood and used. It can be used in a low-code, no-code, full-code environment. We want to provide all those options. It brings together that change detection from the sources and continuous groups and the reaction, the doing something. So it's bringing those together. And also we have this ability to detect when things don't happen, which would require quite a bit of engineering for people to do to replicate that functionality in other systems. And we can run anywhere-ish. But single process, Kubernetes in Docker, embedded. And we are CNCF sandbox, Apache 2, open source, and community driven. And if you want to get going, all of these resources are available to you. The Drasi.io website, we've just re-released that, updated all the information, so it's broken down by the 3 products we have now, Drasi for Kubernetes, Drasi Server, Drasi Lib. We are, as I said many times, open source, up on GitHub. You can come. It's really awesome because we have the community's actually started to grow and become engaged, and people are submitting issues and PRs, and it's really great to see. The getting started on the website gives you step-by-step instructions of how to get started. Well, maybe I'll just jump there. No, I don't have web. Okay. How to get started in a container, dev containers, code spaces, as many options as we could do to make it easy for people to try. There's a tutorial that walks you through, hey, try this, see this. Is that enough? Do you want some more? You can keep going, learning more and more of the features. So we're trying our best to make it easy to adopt and learn. We're on Discord, through that link, and on the website, and you can follow us on any of those systems. And with that, I can open to questions if we've got time.
Any questions? I think this might be
So my question actually is, how do you actually scale Drasi if you need more than one pod or server?
Mm-hmm. Yeah, so there are a number of answers to that. So, how do we scale Drasi? So, the Kubernetes, Drasi for Kubernetes uses the Dapper actor framework, and each query is effectively an actor, or each query host is an actor. The query host can host multiple queries. So that's a way to scale. In Drasi Server, you can host multiple Drasi libs. So a Drasi lib can host many queries, multiple queries. We don't know the limit yet. We've not done that performance testing. But there was 13 in that one, and it was fine. So each instance, you can push multiple queries in, you can have multiple instances, you can have multiple Drasi servers. So we've sort of started introducing Drasi server to some of our active partners now who weren't using Kubernetes, and they're like, oh, great, let's put an orchestration framework around Drasi server. And we're like, well, our answer to that is sort of Kubernetes, but they don't want to use Kubernetes. So they're thinking about how do we get this into other container orchestration platforms. So. So the question is are the connections stateless? How do you mean? Sorry, can you clarify?
So if you basically scale,
Mm-hmm.
if the front-end components do they need to have a connection to the same Drasi pod, or so he actually sticky sessions, or
Right. So some reactions initially were intended to push out into the world, to do something, like to push downstream. These reactions that open connections and allow inbound traffic is a newer concept. So the outbound one is an easy answer. It's just pushing. But in terms of how do we manage sessions across the reactions that expose ports, we don't have an answer to that yet. Yep.
Hello? Hello, can you hear me?
Hi.
Yeah, okay. So I have possibly 3 questions and maybe follow-ups based on those answers on the first question. First one, only because I know what OpenCipher is. Is there a database is there a graph database as part of the Drasi environment?
There is not. We maintain minimal indexes of the elements that we get that are part of, or potentially part of the query result. So if you imagine, when we get the change from the source, we're going to get all of it, right? It's going to send us everything. Our query knows we only need these 4 properties. So one, we just trim it down to the minimal set of stuff we need, and then we index that node, and we index the relations. So we're not using a graph database. We have just like an adjacency list serialized to disk that we use to, and the nature of our graph solving, it works quite well for us. So we've never hit any limits on that, but it's certainly somewhere that, you know, in the future, as loads increase and we get more, we might need to relook at. But we don't have a graph database under the covers.
Okay. The second question has to do with sources. You mentioned, I think you had a few, but you didn't have quite a lot of sources for Drasi. But you mentioned another project called Dapper. So I was wondering, which has a lot of sources, independent even of the cloud. Can those sources be used in Drasi at all?
Currently, no, but we have done some pretty good integration with Dapper, and we're always looking for ways to increase that. And particularly, like with Drasi lib, we're thinking about ways of, maybe building Drasi lib into some kind of Dapper components and sort of providing those capabilities. But looking at, Dapper sources is a great thing we should be doing.
Yeah, I mean, it gets you to more sources without having, while you wait for Drasi sources to come in. So if you can do that, then yeah.
Yep.
And then my last question is, how do you, when the sources have sensitive data and that changes, how is that going to be handled in Drasi?
As in, you're talking about data permissioning?
No, say patient data. Sort of thing, like I said, sensitive data. So if that source has sensitive data and it comes into Drasi, what's it doing to maintain compliance for that matter?
So it's not something we have focused on as we've been trying to build out this technology. We've thought about some things that we need to do in terms of the security model, like always encrypting in-flight data, and our indexes, should be stored encrypted, and all that kind of stuff. So we could do that very easily. But in terms of wrapping it in a more secure and compliant and something that would pass the rigorous tests, we've not even gone down that route. We're just trying to kickstart this idea, and the first period of time was just really validating that this is something people are interested in because they want an easy way to detect and react to change. I think we've got there, so now we're trying to do the grown-up stuff and make it broadly adoptable and faster and more secure. So security and that kind of stuff is definitely on our roadmap, but we've not got there yet.
Any other questions?
Hello, thank you. I was curious about the failure modes and specifically, like, what's the responsibility of the application versus Drasi?
When you say the application, you mean the thing downstream of the reaction?
Yeah.
So it is the goal to get it to a very easy mechanism of the app saying, I last got data at this point and give me everything from now, right? So if that's, I've never seen data before, give me, it should make available a way to get the snapshot it needs and update from then on. So platform has this ability through sequence numbers and being able to ask for the result set for a query at any point in time. So then it's onto the application to say, well, the first event Drasi sent me was this LSN, this timestamp. I now get the results. While I'm collecting the inbound stuff, I build my base set. I integrate the results into that, and the view and React components that we've built and made available sort of do this automatically. But you'd have to do that logic yourself in your app if you wanted to do that. Yeah.
So I just want to make sure I understood that response. So that, let's suppose the Drasi server took a shutdown and
Right.
recovered. It's going to try to recover state,
Right.
But you're saying the app is responsible for some of the housekeeping after
Well,
one of those
the app
incidents?
is responsible for asking Drasi for what it got from the point it last saw it.
Okay.
Internally, Drasi does something similar. And so in the Drasi internals, the source is responsible for being able to get what Drasi needs to bootstrap and to update its indexes if it went down, right? So we internally, and this is a piece of work that's actually unfolding right now, we're making those, there was multiple sort of indexes internally in Drasi. We're making sure all of that is transactionally consistent. So if Drasi falls over, Drasi server in particular, at any point before it's finished processing a change, when it comes up again, it's going to say, hey, source, the last thing I got from you was this LSN, and now the source is responsible for giving Drasi what it needs. And the same mental model is true of what we expect the application to do for us. Ask us for what it saw last. And then,
Okay, that's
yeah.
a clear explanation, thanks.
Okay.
I've got a question. How would this replace or interoperate with an existing event-driven architecture, like something that's driven
Right.
by message queues?
Yep. So, I mean, the thing with events, and yeah, Drasi is an event-driven system, right? Under the covers, we're doing events. The trouble is, again, we're trying to come up to a higher level, introduce consistent abstractions that makes it easier for people to do this one particular problem. Because with an event stream, it's like, here's everything. Figure out what you want, right? Drasi's like, tell me what we want, and I'll tell you when it's changed, right? So you can use some event streams as a source already, and so Kafka is one, Redis we've got. You can use those as sources. There's questions about how you recover from some of those, because not all streams are going to have an ability to look back in time, right? So maybe that source then has to also implement some kind of cache of its own, or sort of like a history. But you can use them as sources, is really the answer. And also you can spit Drasi change notifications out as events, right? Into your, and then whatever's downstream can process it. So I think both sources and reactions can integrate with existing eventing systems.
So your demo example with the stock prices looked interesting, cool, maybe something I'd like to do to learn it. What would you do to set, what available stock feeds, I'm talking about like live stock feeds, are out there that could be hooked up easily to Drasi?
Yeah, I mean, I used, just as a bit of an aside, but along those lines, I used our AI agent the other night and said I wanted a Bitcoin feed, a source. And I said, I just want it to give me, I just want to know about when new blocks are mined. I don't want all of the transaction information, just new blocks. And it did it, right? It just did it. And I was like, whoa, like magic. And so what feeds are out there? I don't know what's, we should provide maybe a list of things to hook it into, but I would say search for a free feed and try our AI agent, which is also already out. It's just a prompt, right? Try the prompt and see what you get.
How does this AI agent compare with the notorious open clause? It's something like that where you're...
No, this is very specific. It's like you've got a developer who's written tons of sources, knows how to write them, and you just say, I want a source that does it. I want a source that integrates with that system there. Here's its API, here's its documentation, and what it's going to do is it chugs away for a while, but it does an evaluation of, is this a likely thing? It does a prototype and validates that the prototype can actually work, and then so that's like the planning phase, and then you implement, and it goes and uses all the stuff it's researched and the prototype, and builds an actual source that conforms to all of the APIs that we use and all the best practices and that kind of stuff.
Is this AI agent a cloud-hosted paid service, a cloud-hosted free service, or something I stand up on my own?
It's a prompt, right?
Okay.
You can just put it into, we use Copilot a lot. I've used Claude. You might need to tailor it because it's sort of focused on how Copilot works at the moment. You could tailor it and give it to Claude, and Claude would probably spit out a source.
Okay, thank you. Any other questions? Please join me in giving a round of applause for this great presentation.
Thank you.
Thanks a lot for coming. It was a good presentation. Thank you. Thanks, Fish.